Good morning. Welcome to warm São Carlos. I mean, really warm São Carlos. It's unfortunately we have a heat wave, which is supposed to decay this week, along this week. It's been really warm. However, I hear from my friends from Alfred that they had been experienced minus 10 degrees Celsius in Corning, so this might be some change for you. Welcome, students. I see different faces here. Welcome from India. You made it, Shweta. Very good, very good. We have this year distinguished professors from Alfred University. Actually, we have 6 faculty from Alfred University, and this is a great, great thing for the school. We also have 2 distinguished professors, visiting professors from Poland. Where is he? I never met. Oh, welcome. Thank you very much for coming. And also Professor Ji-Hong Zhang, all the way from China. He arrived at midnight yesterday after traveling 40 hours, from Wuhan, China. So thank you very much, Professor Ji-Hong. He is the organizer of a similar school in Wuhan. They have had like 5 or 6 schools already, 6 schools in Wuhan every winter. And this is part of an international movement. We have such schools in Wuhan, in Kolkata. I was there a few months ago, and in Montpellier, in France, and São Carlos. These are the 4 top cities in the world for glass. And Alfred, of course. So the next one has to be organized in Alfred. Then we have the 5 top glass cities organizing such schools because, we are training the next generation of students, which is really, really important, the next generation of researchers. Welcome you all. Along this week, we are going to meet each other, and the key word of this series of schools is networking. Networking. So you all have to talk to each other, interact, talk to each other, and networking. I see my old friend Francisco Cervena here, PhD in Oxford University, top guy on mechanical properties, on glasses and glass ceramics, and many top professors that you're going to meet here. So I have a pleasure and honor of introducing the director of this institute, Professor Osvaldo Novaes. He is a very, very well-known researcher in Brazil, a member of the Brazilian Academy of Sciences, and he was kind enough to lend this nice auditorium to us. So Professor Osvaldo, please.
So thank you very much, Edgar. So welcome you all. Thanks. So it's a great pleasure to welcome you here in our home, the São Carlos Institute of Physics, University of São Paulo, which is the home for many of the people from CERTEV. And I just, in addition to saying welcome to our distinguished guests from Alfred University, from Poland, and from China, I also would like to extend the big welcome to the students who come from many different parts of the world. And Edgar said that the main key word for this meeting is networking. I would add that in addition to networking, I would add collaboration and another thing, which is multilateral organizations and multilateral institutions, multilateral initiatives. That's what the world needs, not only for glasses and glass ceramics, but any other area in science and technology and for society as a whole. So I wish you a very productive week here. Enjoy the school, enjoy São Carlos as much as you can, and have a good time here.
Thank you. Thank you, Professor Osvaldo. So later on, I'm going to explain the program in detail during my talk this morning. But now, to get things going, we will start with an introduction of the professors of this school. Each one of them will talk for a few minutes about their background, their research interests, so you students and the other professors will get to know, their research interests to foster possible interactions. That's the idea, interaction, networking. So we will start with our distinguished guests from Alfred, and I'm going to start with the ladies. I think Doris, I'm going to ask you to start, and then Rachel, and then the guys. Do you have a pen drive or? So, okay, Caio, then you volunteered, right? Seus slides estão lá já? If you can, it's best to use this computer. It works better regarding our technician. And also, I have to ask you one thing. All these lectures and talks are on live on YouTube. If somebody does not want the lecture to be online and recorded, please let me know, and then we shut down. If you don't say anything, you are on live. Say hello, because you are all on live on YouTube, and also they are going to record lectures for the website. Everybody agrees? Yeah, everybody agree? Okay. So, you are online, Kyle. Let me just say a few words. Kyle was one of the best students here. He worked here for some years for Professor Ana Cândida. He was supervised by Professor Ana Cândida. Then he went to Germany for some time, became a professor at Cole College, and now, starting a few months ago, couple of months ago, he is now a professor at my favorite international university, Alfred University. So, Caio, I'm really, really pleased to have you here.
Thank you. Hi, everyone. Thank you, Professor Zanotto, for the very kind words. I'm happy that Professor Zanotto said those things. He spoiled it a little bit. I was going to say that it's really nice being here. This is the third version of the school, and I was a student, a PhD student during the first one. I helped organize the first one a little bit on the background, and Professor Zanotto mentioned the networking. I'm still close friends with, I would say, 10 of the students who participated in that summer school. Of course, the other ones, every now and then that we meet, we remember each other and we talk very fondly about this week that you guys are going to go through. So it was an amazing experience, and I encourage you, as Professor Zanotto said, to really connect, mingle, to talk with each other, and to learn more about our community. It's a very tight community, glass science, so you're probably going to be seeing each other a lot. So you better get along with each other. All right? But anyway, so I just wanted to introduce myself a little bit. If you guys are way on the back and you cannot see my face, that's me. What a nice fellow. So my name is Caio Bragato. I am from Brazil. So if you want to speak Portuguese to me, feel free. I actually got my undergrad here at the University of São Paulo as well. So my bachelor is in chemistry, and I did my master's and PhD at Federal University of São Carlos. And then a postdoc in Germany, in Jena, and then I got a position of professor of physics at Coe College, and now I am a professor of ceramics at Alfred University. Just to give you guys a little bit of a background, and of course, feel free to contact me now, later, send me an email. I'm sure you can find very easily this information online if needed. Before I introduce myself, as Doris also mentioned, I wanted to introduce a little bit of Alfred. If you're not familiar with Alfred University, it's a university on upstate New York. So every time that I say, like, oh, where are you working at? And I say New York, and everyone like, oh, I was like, no, no, no. It's a little different. It's a very different. It's a very cozy village, I think is the official title of Alfred. 5,000 students, and recently I learned that around 80% of its population are students from the universities. There are 2 universities there, Alfred University and the State College. So it's a very interesting place to be as a student, as a scientist, as a researcher. And not only that, it's also very interesting because it's very famous for the ceramics and glass, but not only as a science topic, but also as art. We also have a very strong ceramic art program. So here are a couple of photos of our college, and if you're looking for us, I'm hoping this is the laser. Never mind. Oop, it's not the laser. Oh, fancy. All right, so here is where Alfred is on the map. So here, up here is Toronto, and you have Columbus, Ohio, that maybe some of you guys are familiar with from events with the Ceramic Society from the US, and you have New York here. So we are on the countryside. And here is a photo of our campus, very beautiful in fall. I heard, I haven't been there in fall yet. All right, so if you're curious, if you're looking for, I'm already starting to pitch. You guys didn't even know me, but I'm already trying to make you work for me. So we do, as I said, have a very strong program in material science and engineering, ceramics, and also glass. So we have programs in master's and PhD for all of those. And we are ranked among the top 50 material science and engineering programs in the nation and the top 20 specialized research institutions. So it's a great place to do research on if you're looking for a position, if you're interested in exploring collaborations and so on. Feel free to take a quick photo or to search us using the QR code. I would say that for this audience, the 3 biggest programs are going to be the material science, ceramics, or glass. But of course, as I mentioned, we have some other programs as well. I see a couple of people with the cameras. All right, now there's still a couple. No pressure, no pressure. All right, so as I mentioned, we have a strong art program, and if you feel you are one of those students that are walking this line of ceramics, glass, and materials as a medium, maybe for science, but sometimes also for arts, we do have collaborations between the art program and the engineering and science programs. So we have the art engine, which, if I'm not mistaken, is a class between engineers and artists. So yeah, just a couple examples. And of course, we have other programs as well. Great. With all that said, I introduced the institution as the first speaker, and now I'm going to introduce myself. So as Professor Zanotto said, I did my PhD with Professor Ana Candida, and I would say that when I started, it was hers, but now it's also mine. Biggest interest is understanding ionic conductivity in glasses. If you ever had any research on the topic, if you have any classes on the topic, probably saw this equation here in which the conductivity is given by these 4 parameters, each one for a different charge carrier. And my mission in life is to understand what is that value mu and what is that value n. Those are the mobility and the charge carriers themselves. So basically, what is carrying the charge in the glass and how fast that carrier moves in the glass. It's not something trivial to understand. We have a good understanding of what's happening in crystals, but in glasses it's not so straightforward. Just a couple examples of how I approach that problem, how I try to understand that problem. Some of my recent publications have been on pushing the compositional limit of glasses, so trying to work on what we call inverted glasses, going to as much alkali as possible to study that effect, how this high concentration of alkali affects ionic conductivity. Normally, we would expect a linear behavior, an increase in conductivity. Here in the system, you see that we have actually a plateau forming for the activation energy. I'm not going to explain everything right now. If you want, you have to stay awake all the way to the end because my class is going to be one of the last. But this is one of the ways that I try to understand this effect of, or try to understand mobility and the number of charge carriers. Another recent one that we've been studying, this is in press, so hopefully you'll be able to access it in a couple weeks, but is to understand the free volume or the packing fraction within the glass. So we also try to understand how or if the structure affect the ionic conductivity of the system. And these are my experimental proposals, the way that I try to do this in the laboratory bench. Oh yeah, sorry. I also try to play a little bit with the composition by studying something called the mixed alkali effect. If you're not familiar with it, again, during my presentation, I'll talk a little bit more about it. But it is something that's a little bit new to me. So I'm starting looking at the mixed alkali effect as well. Great. And we do this experiments using a technique called electrochemical impedance spectroscopy, which is measuring the electrical properties of a material as a changing frequency as well. And this is something that actually showed up here at LAMAV and at São Carlos, which is I started realizing that this technique could be used more than to just understand the electrical property itself, but could be an indirect way of measuring other phenomena happening in the glass. And that's when I started studying phase transformation. When I was here in São Carlos, we published a work with structural relaxation followed in situ using changes in the electrical properties. So when the glass is relaxing, the electrical property is going to change very slightly, but we were able to follow that change and to relate that to the structural relaxation of the glass. But the original idea that I had was actually to follow crystallization. So to follow the phase transformation from an amorphous to a crystalline material. And this was, when I first proposed this idea, I had a student who presented this work and he made this nice figure explaining the process itself, assuming that you have an heterogeneous crystallization coming from the outer layers. You can actually measure the crystal growth if you know the conductivity of the material at the end. So if I know the conductivity, the R is the resistance to the material that I can get, and if it's an heterogeneous crystallization, I can fix the area, and then I can measure the length. This is a study that I'm very fond of. I'm very excited about the results that I'm getting. And I'm looking for people to work on this. Wink, wink. So if this is something that interests you, please let me know. But I got some preliminary results already. If you're familiar with how transformation of phases happen. And if you're familiar with the graphs, you see that we actually have a very nice behavior of the fraction of transformation here as a function of the log of the time. And you have this beautiful curve. This one is for lithium triborate, 10 degrees below TG. So there is some promising results, but of course, as I said, I need to extend these results. I need to analyze more systems, and so on and so forth. So if you're interested, please reach out. Yeah, and of course, I'm mentioning those as experimental parts. That's what we do in the laboratory. But as you're going to hear from some of the other professors, we also have a strong computational research group at Alfred that I started collaborating even before I went to Alfred. And that created the interest of trying to study this phenomena also through simulations, molecular dynamics. I'm not going to steal someone else's thunder. They will explain it. I'm just going to mention that what we do is follow this Haven ratio, which is the change of the diffusion coefficient, what we call a self-diffusion, or just diffusion through temperature, with the diffusion under the effect of an external electric field. We also got some very interesting results so far. I think we published 2 or 3 articles about it. And again, I want to extend this project as well. But I guess this depends more on my collaborators, because I definitely cannot do this by myself. But here's just an example of the diffusion on 3 different axes of the simulated glass. And you can see that on the x-axis, the diffusion is higher because the slope is steeper here. And this is where we are applying an external electric field. Great. And of course, all this is only possible with my students. So I will say that again. If you're interested in any of this, just let me know. Reach out. Let us talk. I am a very new professor. Right now, I feel very lonely in my laboratory and in my working space. So if you're looking for something like this, please feel free, because without these guys, I wouldn't be able to do what I'm doing. All right? Great. Thank you. Yeah, I'll borrow that. Claro, claro. Thank you. I will try.
Yeah, now we have Professor Doris Monk. Doris, I have met Doris many years ago. She was a student in Jena when I met her. This is maybe 20 years ago or so. And she became very well known. She went to Greece, she went to Finland, to several places before joining the faculty at Alfred. And I'm glad to say that I highly recommended her when they asked me if she would be a nice professor, a good professor at Alfred. So, and I'm glad I did. So she is also a very good friend of ours. She came here to Brazil a couple of times already, several times, and she is a great expert on the optical properties of glasses, colors, and also antique glasses, as I learned from her during my visit at the Corning Museum of Glass. Doris?
Thank you. Edgar just went through my first slide, more or less. So I started my bachelor in chemistry in Munich. I switched to Erlangen after 1 year in Australia. I did my master's thesis on mercury speciation in fish with an Erasmus program in Finland. So I only started working on glass for my PhD at Jena University. And I already, during that time, I started some visits in Greece, and then I got a Marie Curie fellowship for 2 years and stayed 4 years in Greece for infrared and Raman spectroscopy. So before it was more optical properties, irradiation-induced defects in glasses, but now it's everything spectroscopy, pretty much, especially optical, infrared, and Raman, what I'm doing. For NMR, I go to the experts. And then I did my habilitation in Germany 2017. I stayed half a year here in Sao Carlos, then 1 year in Sweden as a visiting professor, and then I settled down in Alfred for good. So that was 2018. So, as I said, yeah, I do a lot of infrared Raman spectroscopy, a lot of structure property correlation of weird compositions, mostly oxides, but also fluoride phosphates or oxynitrates, and especially also what changes happening in the glass as a function of quenching rates, as a function of mechanical impact, indentation, or irradiation, what I started during my PhD. And then, thermal poling, crucible melt interactions. That's a crucible accident on the top, but they're just glasses that are more compatible with some crucibles than others. And Edgar mentioned the antique glasses, and I will get to the borosilicate layer on the Mycenium glass in a little while. At the moment, the research really focuses on the grad students I have and their interest, availabilities, and the funding we have. So Amir was here last year for the summer school. He is crystallizing iotocrystals from alumo-borosilicate glasses, and we are currently doing DSC measurements here with Ricardo in IFSC. So and his transparent glass ceramics, we got some really nice nonlinear optical responses, and while we can't really follow up on those in Alfred, we have collaboration partners in Rochester and Clemson who do. His other project is a really fun one that started during my PhD on irradiation-induced unusual oxidation states like cobalt 3+, nickel 3+. So we tried to get references in chemically derived glasses, and we went to super high optical basicity, and I will talk about that in my lecture. But he now stabilized not only manganese 5+, but also manganese 6+, and now we are looking into other applications, like there's some really good near-infrared fluorescence, and now he tries to tune the composition to a biocompatible one for biomedical applications. I mentioned the ancient glass that was in Greece. The first time I got an archaeological glass piece that was a 3,000-year-old late Bronze Age Mycenium glass. I put it in the infrared spectrometer, and it looked exactly like Pyrex, which we didn't expect. That's melting temperature that shouldn't work at that time. And so after a lot of back and forth, we kind of think that gilding with borax created a borosilicate layer on a normal soda lime silicate glass. With those 3,000-year-old glass pieces, you can't study them very destructively, and you don't get big pieces. So now, years later, we actually got the Corning Museum of Glass to give us 4 little samples. You see one of them on the top. And so we hope to do solid-state NMR to really prove the presence of boron and laser ablation ICP-MS and some other things. And for this one, I have a different PhD student, Annika Blake-Howland, who has a background and a master's in art conservation. So, and she had a half-year, I think, internship at the Corning Museum of Glass as a conservator. So that's a really looking forward starting the research on these 3,000-year-old glass piece. And she's also looking at some medieval red glasses and the Orine glass there. It's always the challenge with the non-destructive testing, and you often have 2 big pieces. You can't break them. They don't fit into the instruments, or you have those tiny little pieces, which are really difficult. And then Kayo mentioned the collaboration we have between the art and the engineering department. So there are always students who want to do some fancy glass colors. So art students who come to our little furnaces and try new things, and we play with them. And students on the engineering side too, they're always excited doing some colorful stuff. So that's a fake lapis lazuli. The color is not cobalt, it's 3 sulfur atoms sharing 1 excess electron. And so, yeah, that's always with the undergrad students, really adore. Lenora is here. There's a poster that will, yeah, she'll talk about the bismuth zinc mix system. They also worked on some really soluble phosphate glasses for bio applications. But Edgar asked me to keep it short, so that's my last slide. So I do dopants, I do all different types of covalent and unusual networks with invert glasses and a lot of conditional glass formers, fluoride phosphate glasses, transition metal ions, usually Raman infrared and optical spectroscopies. Thank you.
Now the next speaker is Rebecca Welch. Rebecca was a student for the famous Professor John Mauro at Penn State. She started at Cole College and then went up to Penn State, and she is now a visiting professor at Alfred University. And I had the great pleasure of collaborating with Rebecca in writing a very long, detailed review article on the Kautzmann paradox. If you are interested in understanding the Kautzmann paradox, ask Rebecca. She'll know everything, all the possible ways to escape from the Kautzmann paradox. I'm really glad that you came here, Rebecca.
Thank you so much, Edgar. It was really great to be here. Thank you, everybody. I'm looking forward to meeting all of you, especially meeting all the students. All right. So a little bit about myself. I went to Cole College and got my bachelor's in physics with Dr. Mario Fatigato. With him, I made lead silicate glasses for my undergraduate research. And then after that, I worked with Dr. Brigado, who was at Cole at the time and is now at Alfred University. So just like he said, something about glass science is that we're a very close community. We are quite a family. So really get to know new people in the field of glass, get to know the professors here, get to know your other students, because they will probably be with you for the rest of your life. And then after that, I went to Penn State and got, oh, sorry about the text, it's all messed up. But I went to Penn State and worked with Dr. John Morrow for my PhD. And in terms of some things that I've done at Alfred University now, sorry, the text is all really messed up here. At Alfred, what I've done is I've really gotten involved in teaching as well as outreach. So something that we're really passionate about at Alfred is connecting with the local communities. So Alfred University is a really small town, and we're in the middle of nowhere. And all around us are these small, little rural schools. And something about rural schools is that they don't have a lot of access to science or STEM education. So something that we're really passionate about is trying to reach out to the schools and teach them about engineering, especially glass science. And so during my time at Alfred, something that we've done is that I've restarted the Alfred Society of Women Engineers. So this was a completely dead club during COVID. But the purpose of the club is to go to conferences. So we go to conferences as a group. During that time, we like to eat a lot of food. That's something that I'm really passionate about. And then we also visit labs at different universities. And then another thing that we've done is we started the Night of Science and Arts. So this is a one-night event that we host at Alfred now. And this is where we bring in about 500 families and students from the rural area. And all of us come together in the engineering department and math and physics department, and we put on a bunch of live demonstrations for all of these little kids. Right now we have about 60 demos, which is kind of on the the small end, but we're always looking for more demo ideas and different ways to get these little kids really excited about material science and all fields of engineering. All right, in terms of my research, something that I really love is using molecular dynamics simulations. So with MD, right, the purpose of MD is we can essentially do everything that we do in the lab, but we can do it much quicker, all right? So if you use MD properly, if you use it well, it can be a really powerful tool to make, say, 150 glasses at one time. You know, typically that would take multiple years. That would take like an entire PhD to study, say, 100 glass compositions. With MD, you can do it in a couple months, right? So that's what's really exciting about MD. And so what we've done here is we've looked at a glass system. This is for calcium aluminosilicates, but specifically we're looking at kind of the extended range compositional end, in which it's really difficult to make these glasses in the lab because they have a very high melting temperature. So we can use MD then to explore these compositions that we can't necessarily make in the lab easily. And so here, this is looking at something called oxygen triclusters. If you have ever worked with aluminosilicate glasses, it might be something that you're familiar with. But this is looking at an entire compositional range. So we went all the way from 30 mole silica, all the way to 80 mole% silica. And this is looking at the liquid state, and we're looking at the formation of these different structures, right, across an enormous compositional range. And what we can do with that is we can use some of these modern day approaches, one of them being statistical mechanics and the other being topological constraint theory, which we're going to learn on Thursday. And what we can do is we can use that information, and for the StatMech model, we can predict what are the structures that are going to be forming. And here, we're predicting how many triclusters are forming across a wide fictive temperature now. For topological constraint theory, what we can do is we can use all of that amazing structural information that we got from MD, and we can actually predict what is the glass transition going to be now across a wide range of compositions. Yeah? So we're relating what we see from structure, and we're using it to predict what happens from real physical glass properties, such as TG, Young's modulus, and even glass hardness. Another thing that I'm interested in is looking at glass fracture and specifically water interactions. So as we might know, water has a detrimental impact on glass. It's very, very bad for glasses. And it's an area that we're still learning about. So something that we can do is we can simulate a fractured glass. And what we've done here is we've created the glass with a notch in it, and then we're inserting water atoms on top and letting those systems equilibrate. So here you can see from the animation a water droplet forming within that fracture. And then what we can do is we can increase the expansion of this notch and simulate a real-world fracture event. And then what we're seeing then is how does water impact the fracture toughness of the glass. Yeah? Another, in terms of developing research, something that I'm really interested in, is trying to use aerodynamic levitation. So this is a very interesting method of glass synthesis. What it does is it uses a giant laser, and what we can do is we can make glasses, and specifically we can melt samples up to 3,500 Celsius. All right, so this is a really cool technique. Only a couple of these exist right now because they're pretty expensive. It's a very niche area. And what we can do, what's really popular right now in terms of research are these high temperature applications, right? So we're really interested in glasses that can withstand high temperatures, high pressures, right? And unfortunately, we can't really make those glasses because they do require such high melting temperatures. Our lab furnaces can only really go up to, 1600 Celsius safely, you know? So we really do need these other techniques to even just make these glasses that melt at a much higher temperature so that we can understand these different glass compositions. Something that else we can do with aerodynamic levitation is we can actually get high temperature calorimetry from it. And then we can also use a very specific method to obtain viscosity and fragility measurements from it as well. Although that's an area that needs a lot more work. But what we can do is now we can couple experimentally as well as computationally studying the structure of these really unique and difficult to melt glasses. All right, and I just wanted to give a quick shout out. So these are the students that I work with. These were students, they're both undergraduate students, so something that I do with a lot of my research is I actually train undergraduates to do my research. So these two, I just wanted to acknowledge them, that they did a lot of these MD simulations, and yeah, and it's a really great area of research to combine experimental and MD simulations. So thank you.
Very much. I guess now I'm going to invite the senior professor of the team, my old friend, Professor Shan Sundaram. We have met many, many years ago, and I'm also thankful to Professor Sundaram because he nominated me for the very prestigious SCOLS lecture that I gave at Alfred a few years ago. So thank you for coming, Sundaram.
Thank you. Can everybody hear me all right? All right. First of all, I want to try my Portuguese. I just learned at the airport. Bom dia. First of all, thank you so much. Thanks, Edgar, for inviting me and the whole Alfred team to São Carlos. This is my first trip to Brazil and to São Carlos. So far, I'm having absolutely great time. So thank you so much for organizing everything. Everything went beautifully for me, and I'm excited to be here. And also, it's fun for me to represent Alfred with all my colleagues here. As Dr. Bragato was saying, we are hiring. We are actually interviewing candidates now. With success by fall, we'll have one more new glass professor and one more new ceramic professor will join full-time at Alfred. So you'll hear all about it in the future. Those who have been to Alfred, you already know a lot of quirky things you've heard here. But you have not been to Alfred, you are welcome anytime. And this is the best way, the one word can describe Alfred is zen. I'm going to say that. So because people think if you just land in New York City airports, noisy, everything, and then you just take this long ride to upstate, it's very quiet, very zen, and lots of glass and ceramics. Okay, with that, let me briefly present. I'm going to present a little differently. I'm only going to talk about the new capabilities we have in my group and at Alfred. One of the things you may already know is Alfred is very equipment rich. We share all our equipments commonly by all faculty and professors. But I wanted to talk only about some of the equipments we have in my group or related to my group so that you will know some new facilities we do have. And if you have some ideas for which you need those equipments, you can access them. Give me a minute. I think mine is somewhere here. I get the pointer? Could I get the pointer, please? Maybe it's here. Yeah. Okay. Let's move forward, right? That's forward. That's backward.
In the laser, you have to hold it a little bit.
Okay. All right. Thank you. Thank you. I thought I will talk a little bit about the facilities and unique things I have in my group. And I'm one of those professors who are at the interface of ceramics and glass. I also do research on ceramics. And recently I have a project on cermats, where you can combine ceramics and metals for nuclear application. But I am equally interested in glass. And you can see broadly, I am interested in any light interaction with the glass and ceramics, cutting across from anywhere from visible to all the way to terahertz frequencies. So one of the things you may know is there is plenty of spectroscopic techniques you'll come across, which is very useful for glass. But you may also know these spectroscopic techniques give you snapshots of structure through various processes going on, but you're also getting window of your glass structure in IR and UV visible and some of these windows, in my opinion. What I'm trying to do, I'm very interested in connecting structured properties, particularly structure using all these known spectroscopic techniques, and connecting them to some of the long wave spectroscopies, millimeter wave, terahertz waves. Why, you may ask? I can elaborate a little bit more in the talk. I don't want to take too much of your time. I'm very interested in connecting a glass structure to long wavelength properties. Let me put it that way, so that it'll kind of put it a little bit different. And the tools and techniques are available, and some of them are available at Alfred. You're welcome to use. So since I have arrived in 2011 at Alfred, some of the facilities I've been helping to assemble, you can see those here. This is terahertz millimeter waves in glass research. I will be giving a tutorial on terahertz properties of glasses on Thursday. Feel free to ask questions at the time, more detail. I'm also very interested in applying short laser pulses to materials, particularly also to glasses. I'm talking about femtosecond pulses all the way to even artosecond pulses. I have interest recently on that. The reason to study pulses is you can pack a lot of energy in photon packets, and you can deposit into glass. One of the good things about glass is it's mostly transparent in optical wavelengths. Of course, there are a lot of glasses which are not transparent in optical wavelength. So lots of laser pulses can be coupled to optically transparent glasses. You could also couple them to optically not transparent glasses like chalcogenides and some of the other glasses. So I've been doing some work on that. We have published quite a few papers in these two areas. If you're interested in any of them, I would be glad to just send you the PDF of papers, so you don't have to waste your time looking for them. It's just easy, just ask me. I'll email you so that you can, instead of looking for it, you can actually read the paper. The third area I'm working on is additive manufacturing or extreme manufacturing, and some of them are more applicable for ceramics, but I'm very interested in exploring any way of applying those tools to glass manufacturing. So these are the labs I have, which is I do have the terahertz spectroscopy lab. Sorry, it's not moving. Where I do have a spectrometer and imaging scanner. You could use that. And I talked about the laser. I do have the 40 femtosecond pulse laser system. The two other areas are the gyrotron. The gyrotron is a very high energy system where you can deposit high energy, long wavelength into materials, including glasses. I'm very interested if someone is interested in studying gyrotron radiation on glass or applying gyrotron radiation into glass. One of the things these high energy can do is you can introduce highly non-equilibrium effects in glass. just like any material, you can shock the material and make it do unexpected things. I'm very interested in that. And I do have the Lithos 3D printer for ceramics. We use it mainly for ceramics, but you can also use it for possibly glass powders and also glass ceramics, possibly. Once again, our goal is to make these capabilities available for everyone. I have funding from all these various agencies. Before I came to Alfred University, I was at Pacific Northwest National Laboratory. I still have a lot of DOE connections and DOE money. So because of that, I keep getting a lot of equipment money. I wish they gave me more research money. So they always give me money to buy new equipment. So I end up buying more, okay? So this is a spectrometer I talked about. Just for the benefit of everybody, I will make it quick. I don't want to take too long. But I will be talking about the spectroscopy results for various glasses we have published in our group. So I can elaborate more at the time. This is the lab in which you can see that's a spectrometer right here. And this is also a scanner attached to that. That is Nicholas, one of my grad students. The other terahertz equipment we got 2 or 3 years ago is TerraSense, which is a scanner. It's a dual terahertz camera, and you can use it to scan. And terahertz, by the very nature of long wavelength, you will not be able to get atomic scale or those bonding information, but you'll be able to get large-scale phenomena going on. If there are large-scale resonances happening in your glasses, or if there are biomolecules coming in contact with glass, biomolecules and several organic molecules have significant signature resonances in terahertz frequency region. So this camera can be perhaps used for scanning and looking for large features in glass, ceramic, or any other dielectric material mostly. This is a laser system I'm talking about. It's 40 femtosecond pulse laser. You probably would have seen plenty of papers on using femtosecond laser to write structure in glass, which is well-known field. You can write, you can nucleate and grow crystals where you want to. There are some fantastic papers have been already published. I'm more interested in really seeing, can I locally modify the glass structure? I'm not that interested in either writing a structure for an application, and this has also already been well done. So some of the research we have completed, we have shown you can change local coordination of glass structure in the location where you are applying this laser pulse radiation. And you can also, at least one property we were tying it to is hardness, surface hardness of the glass. Again, I can show you those publications later if you're interested in. This is the gyrotron, the high energy equipment I talked about. Physically, I have moved this to the company which manufactured for us in Massachusetts, US, but we have full access to this. This is a 95 gigahertz, 10 kilowatt. You can deposit that high energy into glass or ceramic for about, it comes as a continuous wave, CW, so you can apply for a few seconds if you want. So as I mentioned to you, I'm more interested in studying what are the non-equilibrium things you could do to glass, ceramic, or any material preferably at room temperature. The last is the Lithos 3D printer. This is more for ceramics, but this is in our digital fabrication facility. I bought this mainly for ceramics. You can use ceramic powders, but as you know, there are many research groups use ceramic and glass powders. They make composites. So if you're possibly interested in exploring some 3D printing aspect, only using this technique. This technique uses lithography. I just wanted to clarify that. Then you're welcome to visit us. With that, I'd stop here. If you have any questions, you can ask me anytime. I'm going to be here until Friday. And once again, thank you so much for the invitation. I appreciate being here, and I'm excited about Alfred Sakaula's collaboration. Thank you.
Thank you very much. I guess we can move on. Colin, would you please come here? Colin is another of these bright students from Cole College. He has a similar history as Rebecca. Started at Cole College, was the famous professor Steve Feller, good friend of mine, and then went to Penn State, worked for John Mauro, and he is now a professor at Alfred. Colin is an expert on computer modeling. He is being interested, I guess, well, he is going to talk in more detail on understanding the glass structure, relaxation phenomena, and also my favorite topic, crystallization phenomena. So thank you very much, Colin, for coming to San Carlos.
Thank you, Edgar, for having us. Exactly right. So I'm going to go ahead and go through my background a little bit. Right off the bat, I want to thank my students. This was our last group photo. Somehow I've amassed a large group, totally on accident, but I'm always looking to expand as well, if you're so interested. Yeah, so just a little bit about my background. I actually went to Cole College, and that was because I was obsessed with particle physics initially. And I was really blessed to have an internship in Germany, in Hanover, at the Albert Einstein Institute, and found out I hated the particle physics community, had a terrible time. So I was already at Co, so I was like, glass is it then. So I went to Glass, I went to Penn State to work with John Mauro, and then I actually worked in a startup company for a couple years called Glassworks, where we were using AI to predict how we could combine different waste streams. So maybe we have some bottled glass over here, maybe we have some coal ash over here that's a waste. How can we mix these things to produce new glasses? And how can we use machine learning to predict what things to combine and what is the value of what we're getting? So we raised $30 million and we built a factory in South Carolina. Actually, being here in Brazil reminds me of being in South Carolina in the summer. So, you know, it's nice. And then, of course, after that, I went on to become faculty at Alfred, where I've been ever since, which I really have loved my time at Alfred so far. So my group is split largely in two. So half my group is really focused on sustainability because I come from this recycling background, from this recycling startup. Half my group, especially the engineering-minded students, really still continually work on sustainability of glasses. And then the other half of my group is really interested in the physics of glass, or how do we model this? How do we build new approaches to modeling old problems? So when we think about sustainability, of course, there's multiple challenges, right? In the US, we have a big recycling problem that's not obvious how to fix. We have issues related to manufacturing. Of course, you know, 1 pound of glass will produce almost 0.4 pounds, or 1 kilogram of glass will produce almost 400 grams of CO2, depending on where you produce it, how you produce it, and what kind of furnace you're using. And then also we have issues near the renewable applications. Glass is quintessential to many of the clean energy technology that we're working on, right? If we think about solar panels, glass is by weight the most important thing in the solar panel. If we think about windmill turbines, those blades are made out of fiberglass that have to have incredibly high Young's modulus, incredibly high. How to make such a thing is a large challenge. Of course, we also have more traditional insulation, you know. Fiberglass insulation is still a large challenge, and the issues underlying the theory of fiberglass are not well understood. There's still a lot of work to do just in the understanding of thermal conductivity and mechanical understanding of how we produce fiberglass. My students always laugh at me. I'm a huge fan of window technology. I always go off on about windows when we talk about sustainability, which I'm sure all of my students love, right, River? Thank you. So, of course, there's still it may sound silly, but there's still a lot of improvements to do with windows. How do we make better windows for better heating and cooling buildings is still a large challenge. And these are glass challenges. It's not just coatings challenges. There are real challenges related to the glass, related to the sustainability of the industry that we call a home. Of course, I'm also interested in the modeling of glass, especially non-equilibrium processes. So when we think of, you know, the traditional approach to non-equilibrium processes, we think of Onsager reciprocity, right, Ben? Yeah, Ben is always telling me about ensemble reciprocity. That was a joke. That's fine. Anyway, so, and the truth is, ensemble reciprocity is essentially a Taylor series expansion where you truncate after the first term. And so it's not an accurate description for anything that's very far from equilibrium, like we know glass is. So we need alternative approaches that go beyond the traditional approaches of non-equilibrium calculations. The other thing I can't stop talking about is energy landscapes. If you ever take a class with me, you'll learn a lot about windows and you'll learn a lot about energy landscapes. Those are the only two things I can promise I'll teach you. But this idea is about if you can find all of the ways of arranging atoms, you can find the energies and the associated barriers, and from there you can make many calculations. When I talk about relaxation, we're going to go fairly in depth into energy landscapes, and we'll talk more about that on Thursday. But also, we're trying to expand this idea. So for instance, over here, this is what we're calling a fracture energy landscape, which is if we have a crack that propagates through some area, dl, what is the change in energy that we expect? And can we back calculate the fracture propagation, the fracture pathway, without ever carrying out an MD simulation? And the answer is yes. We are actually able to now predict fracture toughness within just a few minutes based on energy landscape calculations. The last two things I really want to talk about is since I've came to Alfred, I have really spent a lot of time on our undergraduate research program, along with the other new faculty and other faculty. When we started this program, before we started this program, there was only like maybe 4 or 5 students a year doing research. And now at Alfred, every summer we're having 45 students, 45 undergraduates doing research in our labs. And so we fund them all, we encourage people. We've actually ran out of internal students. So if you're so interested, please let us know. We're always looking for more students to spend a summer with us. This is really exciting. This is actually, we have a poster session at the end, which is shown here. We have different professional development talks given throughout, and this is actually a tour. The picture on the bottom left is actually a tour we did of Guardian Glass's premier facility and OI. It was a long day, but we got to tour both very good factory tours for all the students to go and see. With that being said, thank you so much. I want to say that I've been really thankful for all of our sponsors who are shown on the screen, who have been able to support my group and our ongoing work. With that, thank you so much.
Thank you very much, Colin. Ben, yes, well, I guess we move on. And this is Benjamin Moulton, professor at Alfred. He spent 4 years in São Carlos. 4.5 years in São Carlos, working with Professor Pisani, who is sitting there. He is a Raman spectroscopy expert, and it's interesting that we met in Buffalo, in the USA, in the physics of non-crystalline solids. I was very impressed with Ben's presentations. You were a student at the time?
Yeah, that was third year PhD student.
He was a student. I was impressed with his presentation. So I gave him my card and said, hey, when you publish your articles, please send me a copy. But that way we started somehow to collaborate.
Yes.
And in the end, he came to São Carlos for his postdoc studies. And now he is a professor at Alfred. So I'm proud of you. Thank you for coming.
Yeah, and I'm really happy to be here. So I just like to echo that point that Edgar's making. You know, it started with a one-line conversation. Edgar turned around and said, here, contact me later. For those of you in your third year of your PhD, you know that the third year may not always be the end. So it was actually some time before I reached out, because it took me another couple years before I finished my PhD. So a year later, when I was almost done, I reached out, and eventually that led to a FAPESP scholarship here as a postdoc. So things that start here will have a multiplier effect as you go forward. Absolutely. Where's the thing here? Is there a... Anyway, I'll use this. Oh, there it is. Okay. Laser is
this one.
perfect.
You have to hold it.
Good. All right, so I'm Professor Ben, for those of you who are here. You're welcome to speak to me in português. Posso falar pouco português, pouco básico, então falo devagar, por favor, pero vou entender você. So yeah, since Caio joined a couple months ago, I'm the newest professor at Alfred University, and I love traveling. I intentionally wandered and got lost a lot, so every green dot on here is someplace I've been, worked, traveled, made friends with, and I hope you guys have some of those experiences. I'm a Canadian, so I started my degree up in this little corner of Canada. I did my master's and then my PhD at the University of Toronto, and that's where I met Edgar at a conference just across the border in Buffalo. From there, I had a great desire to come south. I had connections to Latin America, and I asked myself, where's the best place to do glass that's also really warm? And that was Brazil. So that's how I ended up with Edgar, wanting to get away from the winter for a bit. I spent 4.5 years there. I left in 2021 during the pandemic, unfortunately. It was quite sad to leave during that period. But I had an option in Germany, so I continued with another postdoc at Friedrich Alexander Universität with Professor Dominique de Ligny. And from there, shortly after I got to Germany, I had an interview with Alfred, and that's where I've ended up about 1.5 years ago at Alfred University, that little dot that you've seen in a couple presentations now. Glass attracts the very amorphous people, pun intended. I'm a geologist by training. Lots of your physicists and chemists and engineers. I'm perhaps one of the only geologists that lost my way and ended up getting stuck here. So that's me sitting by a volcano during my PhD in Iceland. And for my PhD, or for my master's actually, I ended up studying rocks that were 2.7 billion years old. And I saw this thing here. For those of you who haven't seen it, this is a typical conchoidal fracture related to perlite rocks. Okay, and from that captured my mind about glass, and I decided to do a PhD at Toronto with Professor Grant Henderson, working on glasses. But he couldn't take me right away, so I had to find something to do for a year, and I had made friends in Ethiopia. So I hung out with some other friends in the wilderness before doing a PhD in the structure of glass under high pressure, doing diamond anvil cell work. From there, glass structure was it. It's my passion. I love thinking about glass structure. I haven't put a lot of examples because tomorrow morning, first thing, you're going to see a lot of Raman spectra that I've taken. But anything to do with glass structure falls into my interest. And you may be familiar with this image. This is a crystalline SiO2. And this is a depiction of amorphous SiO2 by Zachariasen back in 1932. And in 2012, there was some accidental TEM work here where they were depositing non-silica onto carbon substrate, and they got these images, and they said, oh my goodness, we better publish this in the glass community and look at the similarity between what Zachariasen predicted back in 1930 and what we see today with TEM. My main expertise and what I spend a lot of my time thinking about is Raman spectroscopy. Again, I'll show you this tomorrow morning. I've done quite a bit of X-ray absorption spectroscopy, and recently, just last week, I started doing PDF with neutron diffraction at Oak Ridge National Lab. The other thing I'm interested, because structure is one of those weird things that you can do a lot of structure and you still don't even come close to touching all the parts of glass. It changes with the thermal history, it changes with how fast you freeze it. And so I've been tasked at Alfred with looking at different forming processes. So one of the things that I would, then here's another plug, if anybody's interested in doing a PhD, I've been tasked with getting this industrial scale fiber draw tower up and running again. There was a couple PhDs done about a decade ago, and it hasn't been working, so I'd love to get a PhD student who's willing to help me rebuild it and look at fiber drying processes. This is kind of a unique setup. It's one of only 2 in the United States, and we have a silica furnace and a soft glass furnace for doing low temperature fibers. So it's quite unique capability to look at fibers that you can't easily produce, and certainly the reproducibility of fibers not done with a draw tower is quite difficult and challenging. The other thing I've started to do, this is the levitator that you saw. This is a little bead of a silico-tungsto-phosphate glass, and I've started making levitation beads as another way to produce glasses that have extremely fast quench rates, and looking at the effects of their structure and relaxation, those techniques. So to do some of the PDF analysis and the X-ray absorption, you need large national labs. These are experiments that are almost impossible or extremely challenging to do on the lab scale. So I tend to do a lot of work involving national labs and synchrotrons. This is a picture of the synchrotron Spring 8 in Japan, where I did some measurements during my PhD, some high pressure inelastic scattering measurements here. And here's another picture of Canadian light sources. So a lot of my students who end up doing X-ray absorption or PDF analysis will end up going and collaborating with researchers at national labs across the US and potentially worldwide. So anybody who comes to work with me, that will be the options you've got. Again, I'm going to show a bunch of examples on Raman tomorrow morning, and later in the week I'll be talking about some ion exchange work that we're starting up. So, muito obrigado, thank you very much. I'm so happy to be back in São Carlos. It's a real honor and a pleasure, and I never knew this day would come, so it's quite surreal to be here now. So thank you very much.
Thank you very much, Ben.
One last thing, sorry.
Yeah.
I wanted to say, Kaio gave you a brief introduction to Alfred University. This year is our 125th anniversary, so we have tons of celebration going on. And just as an added incentive for the students out there, we're going to pick each day any student that has a nice question, a good idea, an insightful comment. We're going to be keeping track of you, and you will have the option to get this lovely shirt from Alfred. And later in the week, if we run out of sizes, or if you prefer a coffee mug, we also have those too. So we'll be choosing this at the end of each day.
Can the professors compete also for the shirts? Well, now I have Professor Thomas from Poland. This is reaching out. This is networking. Professor Thomas saw the advert of this school somewhere in LinkedIn or something. Have we met before?
Yes, we met in Oxford.
Oh, in Oxford. In Oxford, several years ago. No, last year I was in Cambridge. Oh, Cambridge. Oh, in Cambridge. Okay. So he was interested in this school, and he said, can I also attend this school and bring 3 students from Poland? I said, yes, of course. Yes, of course. So that's how this small glass community, the glass community works, you know. So Professor Thomas, thank you very much for coming, and look forward to hearing your short talk first, and then a longer tutorial sometime this week on Friday, I guess.
Thank you very much for warm reception and giving this opportunity to be here and give the longer lecture on Friday. So, yes, my name is Tomasz Pietrzak. I'm from Solid State Ionics Division at the Faculty of Physics, Warsaw University of Technology in Poland. And as I guess most of the people here are from South and North America, let me give this opportunity to introduce Poland and Warsaw a little bit. So as you can see, Poland is in Central Europe. It is not that far away from Brazil, from São Carlos. It's only 10,000 kilometers Well, actually, Alfred is 7,000 kilometers. So we are not that far away, not much far away than Alfred. And we had a nice trip with transfer in London and then coming here to Sao Paulo. So here are some pictures from Warsaw. Warsaw is the capital city of Poland. It's rapidly developing. We have a very modern city center with lots of skyscraper. Their number is growing and growing still, as well as we have pretty nice old town with the royal castle, city walls, and so on and so on. Actually, what you see here, almost everything was rebuilt after the Second World War. So the city was totally destroyed in 1944 and rebuilt since then. So very nice place, I guess, to visit. Warsaw University of Technology is said to be the best technical university in the country. We have about 20,000 students, I mean bachelor and master students. The university was founded in 1915, but actually the tradition of learning science, learning engineering in that place started in late 19th century under different name and different organization. We have 19 departments. We have approximately 800 PhD students. Most of them, I guess, are from Poland, but the doctoral school wants this school to be as international as possible, so everybody is welcome to join our doctoral programs. We have the growing number of classes in English, so everybody is welcome. Do you have a question? No. It looks like having a question. And also we have some funding to invite PhD students. So if you are already a PhD student, but you find collaboration with us interesting, we have an opportunity to invite you for a couple of weeks to spend with us, and we can cover the costs. And also we have growing number of funding to send our students abroad. This is why it was possible for my students to attend the conference, this school here. In total, we have about 2,500 faculty, including 500 professors. And I guess only 3 professors working on glass nowadays. So moving more to my research interests, it's obviously glass, but it's quite wide, I think. The main topic is synthesis of oxide glasses, mostly phosphites, containing transition metal oxides and rare earth elements. And my group observes several phenomena in those glasses. So basically, we study giant increase in electrical conductivity as a result of thermal nanocrystallization of glassy analogs of cathode materials for lithium and sodium-ion batteries. And I will cover this topic in more details on Friday. We also investigate stabilization of phases confined in nanocrystallites embedded in residual glassy matrix. We study some glassy phosphors containing rare earth elements for white LEDs. And recently we started to use molecular dynamics to study glasses subject to high pressure. So I will not describe our research in details now. I put many stress on inviting bachelor students into research. So I will show you several snapshots, several papers where bachelor and master students had very important role and could co-author those papers rather than describing the research itself. The first topic, which is nanocrystallization and increase in electrical conductivity, will be covered on Friday. So I will talk a lot of this, how nanocrystallization leads to increase of electrical, mostly electronic conductivity, but it's not a secret that it is correlated with the appearance of very small nanocrystallize in the glassy structure. We also try to test our nanocrystalline materials in sodium or lithium-ion batteries, and we try to show that they can have a pretty nice electrochemical performance. Another topic is stabilization of some phases that should not be stable at room temperature. And one example is bismuth oxide. And the delta phase is normally stable above 730 degrees, but in glassy matrix, it can be stabilized down to room temperature. And once again, very small nanocrystallites appear, and they have, we believe, deciding role in this phenomena. This topic will be more covered by Maciek, one of the students who is here, so you are very welcome to talk to him later on. Another field of interest are optical properties. We managed to synthesize some phosphate glasses with europium oxide, and only by altering the reduction atmosphere during the synthesis, we could strongly affect photoluminescence properties. So on the right-hand side, you can see photoluminescence of the same glasses. The starting composition is exactly the same, but we introduce either weak or strong reduction atmosphere during the synthesis, and you can see that in the top picture, we see the luminescence from europium 3+ ions, but when you go down, you got pretty nice warm white luminescence properties, then cool white, and we also have fourth pictures when the luminescence is blue. So we can pretty nicely tune the final color, the final spectrum, only by proper reduction during the synthesis. And another topic is molecular dynamics. So we started to study silicon oxide glasses under high pressure and determine their thermal conductivity. The recent topic was also to synthesize nano glasses. So each particle in this system is amorphous rather than crystalline, and we studied the thermal properties and some other properties of such systems. During the networking in Cambridge last year, I also learned that there is a group in France that's trying to synthesize such materials in experiments. So once again, that was a very nice example how networking allows you to find friends that work on the same topic or something complementary. We do numerical studies and they do experiments. And if you are interested in this topic, another student, Adam, will have a poster on this. So he will be also very, very happy if you come to him with questions. So a little brief description of our methods and laboratories that we have either on site or we have some close collaboration with our colleagues. So we have a laboratory of glass synthesis. We have different furnaces and we can reach temperatures as high as 1700 degrees Celsius. We can introduce reducing atmosphere as well up to some lower temperature actually. We have X-ray diffractometry. We can take measurements also in situ during heating to high temperatures, and also we can cool our materials down to liquid nitrogen temperatures and conduct X-ray diffraction. We have thermal analysis laboratories, so differential thermal analysis or differential scanning calorimetry, also with modulation and thermal mechanical analysis. In our laboratories, we have pretty long experience in impedance spectroscopy. My senior professors were very, very good at this technique. So we have several impedance spectrometers. with the frequency range below 30 megahertz, and we can cover the temperature range from minus 170 Celsius, so once again, approximately lithium nitrogen, up to 700 Celsius degrees, and we can conduct the measurements either in air or in argon flow, I mean the heating rate range with argon flow. Our colleague has a Raman spectrometer as well, and we collaborate closely with some groups nearby. So we have a group in Lithuania who can conduct impedance spectroscopy up to 10 gigahertz, and is sometimes important to track especially electronic properties within this region. We have electron microscopy, SEM, TEM. For X-ray absorption, we started to go to Solaris Synchrotron in Kraków, southern Poland, when we can collect XANES and EXAFS spectra. And our colleagues from Gdańsk, it is north part of Poland, the Baltic Sea region, they have X-ray photoelectron spectroscopy available for studies. And just to show you some international collaboration, so we collaborate with groups in upstate New York, Rensselaer Polytechnic Institute, University of Waterloo, Canada, Queen Mary University of London, University of Lille in France, and the mentioned group in Lithuania, and National University of Singapore. And I hope that this map will have more and more dots after this wonderful meeting. And just to finish, the group is hopefully building and increasing in the numbers of students. Recently, the professors Jerzy Garbarczyk and Marek Wasiucionek went to, or are about to go to retirement. So now I'm leading the group, and we have several PhD students at the moment and several master students. Sometimes it's quite difficult to attract new students because many of them prefer to go groups that work on crystalline materials, on some nanomaterials, carbon nanotubes or something like this. So we need to do a lot of PR to attract people to glass science. But from these pictures, you should recognize Maciek, Krzysiek, and Adam, who are here. And unfortunately, the girls couldn't be here with us today. Yeah. And that's the last slide. Thank you for attention, and I hope to meet you and have a nice time here. Thank you.
Thank you for coming in and bringing three students. I really appreciate this. Very good. Thank you. Professor Zhang. As I said before, Professor Zhang is the organizer of this famous Wuhan Winter School of Glass. I had the pleasure and the honor of attending one of them last year. This year, was this year?
Last year, in fact, it's last year.
Was in
2024.
24, wasn't 24. Wasn't 24. But was superbly organized and spectacular school. So I learned a lot from your strategy in organizing such schools. So it's an honor to have you here.
Yeah. Thank you, Professor. May I just 1 minute to use the USB drive? Okay, I can find it. Yeah, I found it. Let me take a look at the file name. Oh, oops. Where is? Oh, here. Name.
Okay. Oh, good.
Yeah.
Slide. lasers.
Yeah, yes, yes. Thank you. Okay. Thank you, Professor Nanzhuang. In fact, it was my honor to invite you for our winter school. It's my honor. And also, Professor Noto said I'm a good school organizer. In fact, I will try to prove I'm also a glass researcher. So here is something about our research topic. Just in my group, I come from Wuhan University of Technology. It was in the middle of China. It's the Yangtze River. You know the Yangtze River is very famous in China, cross the city. And also in our university, we have a dedicated laboratory of silicated materials for architectures. We focus on the silicated materials, including glass, concrete, cement, and also ceramics. And most recently, our state laboratory separated into state laboratory for the reorganizing the laboratory. So now we have two state laboratories. The first one is the same name, State Laboratory of Silicated Glass here for architectures. Now we have one more new state laboratory focus on the advanced glass materials. So another state key laboratory. So I'm in the new state laboratory, the state key laboratory for advanced glass materials. Just recently we changed. So, in fact, my topic is just my team topic. We have a very big group, glass research group, and also famous professors, including Professor Xiu Jianzhao. Maybe you guys know him. He's quite famous in the glass and thin film coating on the glass. He got the ICG Gotthardi Prize in 1998. And my research topic about high-strength glass, transparent glass ceramics. In short, we are making cover glass for cell phone. How to improve the strength. If you are using a broken cell phone with broken glass cover, that means your glass is not strong enough. We are trying to make stronger and stronger, and we are using glass ceramics. I think maybe the Corning guys first developed the product like a ceramic shield. Now we are improving the quality. The second one about my research topic is about plasma melting, ceramics and the glass microsphere. In macro scale or nano scale, we are using plasma to melting. The highest temperature can be reached 10,000 degrees C. We are trying to use this technique to find some new glass system, including aluminate glass, new aluminate glass. In fact, last year, Professor Noto brought up an idea about how to make the transparent component glass and ceramic sphere. We put our transparent microsphere in the glass, and Professor Noto will use machine learning to design the glass composition with a similar refractive index. Unfortunately, we are trying to improving our technique to make a full transparent microsphere. So sorry for the delay. I also remember your excellent idea. So the second one, my talk is about the glass fiber-based sensitive surface enhanced Raman spectroscopy for sensors. We are trying to decreasing the detection limit up to 5 more percent, 10 minus 15 more percent for the low concentration detection. In future, we are using it for the chemical sensing, for the health monitoring, and some other things. And we also doing some research on Sogel process. For graded or gradient refractive index, we use the layer-to-layer stacking technology to use a different composition. That means the different refractive refractive index. We coating layer by layer and make a bar glass, and finally make a bar glass. And in the first page, you can see I have 3 affiliations. Oh, sorry, I'm trying to, what's it? I'm trying to find the first page. My affiliations are the third one. We call the Herpu Research Center for Silicon Materials Industrial Technology. It was in Beihai City. Because we have a research center in the south of China, we focus on my next topic, glass for solar panel power. You know, the solar cell panel is very useful and very, how to say it, many kind of products in nowadays. So we focus on solar panel glass cover. We're trying to make pretty thin glass, less than 1.5 milliliter, to make the solar panel lighter and lighter. And also, on the solar panel glass, we are trying to make anti-reflection coating to improve the transparency. Now the best transmittance for our coated solar panel glass can be get to like 96% transmittance. Okay, here is, in fact, I have one more. Where last year I got a national project to developing high modulus glass fiber. We're using non-alkali silicated glass for the high strength and high modulus glass fiber using for the wind electricity, you know, the windmill, like that. So we are trying to developing that kind of, the highest modulus can are higher than 110 gigapascal. It's just several topics about my glass. In fact, there are some detailed contents. If you are interested in our topic, we can talk in the whole week. I will always be here. And beyond my research topic, in fact, we are trying to find some international students and international postdoctorate in our group. If you are interested in our research, please contact me. You can find my email address in the first page, my email address. Here it is, my email address, OPTINFO. It means I make it short, optical information, so I make it OPTINFO. Okay, here is my address. And also one more thing, one of my duties here is trying to find some potential participants for this year's winter school. Professor Anna, we are organizing this year's winter school. It will be in November 2nd to 8th. Please keep the date, save the date. November 2nd to 8th, 2025. Yeah, so we will make the first announcement soon, maybe the end of March or beginning of April. So I will distribute our announcement in the ICG website and also by some emails. Please join us, including potential professors and students. Okay, we are trying to make our winter school more and more international. It's our duty, Professor Anna. Okay, thank you.
Well, thank you all for your presentations. I'm going to briefly describe the program, go through the program. So we have a clear view of this week's activities. We started here with the international professors' introductions. After break, in 10 minutes, we have a coffee break, and then we have our CERTEV professors giving their views on their research experience. And then we have lunch. And there are many restaurants walking distance from here. I suggest that you follow Brazilian students. Brazilian students will lead the way, you know, to the restaurants here. We have Ricardo, please stand up. Ricardo here is one of the organizers. He did a lot of work to organize this school, and he is going to join us. Who else from São Carlos here that can lead the students? Albert, are you going to have lunch here in the city? Huh? You are going to be here in the city? Huh? Não. Edu, você vai ficar aqui? Você vai para casa. Who is going to stay here? Today I cannot stay here. I have to go to a university to get some money for you. Unless you want me to stay here, no problem. But I have to go to a bank. So only Ricardo. Only Ricardo. Hein? Respondendo. Álvaro. Não, o Caio. 10 years ago, but you can find your way to Praça 15, right? You can help. Around Praça 15, and you also, Ben, around Praça 15, there are many possibilities there, different restaurants. You should try different restaurants. Tomorrow I'm going to join you, but today I cannot do this. So you have the three guides, Caio, Ben, and Ricardo for today. Follow those guys, you know, and for lunch. And then in the afternoon, we have the fire talks, you know. If you're brave enough to give a fire talk, it's 1 minute to advertise your poster. That's the idea. You just advertise your poster, which is going to be on display during the long coffee break in the afternoon. In the afternoon, we have a half-an-hour coffee break where you can display your posters, and they'll be hanging there until Friday. So interested people, other students, and faculty can go and talk to you in your posters. And we have a surprise to you. If you're brave enough to give a fire talk, some people do not want to give a fire talk, okay, but you'll not get a nice gift if you don't give a fire talk. Professor Ana is going to chair the session, the fire talk sessions, because I have to go to university to get the money sorted out in the bank. But you share it and you give the gift to those who give the fire talk. Always. Also, if you give a fire talk and you present a poster, you have a special certificate that you presented a poster. And this can go to your CV. I mean, it's an international meeting where you gave a poster. This adds to your CV. You know, you see how important it is to add to your CV. Things are very competitive these days. If you want to apply to a postdoctoral position or to a professorship or to any job, CVs are very important. Anyway, so the strategy is that every afternoon we have a long break where you present your posters, except for tomorrow. Tomorrow we are going to visit our glass labs at the university, and the day after you have a tour. If you have chosen to take the tour, these are not compulsory activities, but so tomorrow to go to university, there will be vans, shuttle buses at your hotel. Just after lunch, go back to the hotel, and the shuttle buses will be waiting for you the day after tomorrow and the day after tomorrow. Of course, we have several lectures. Tomorrow we have the tutorial lectures of different professors, but I'm just emphasizing the extra activities. For instance, tonight we have a welcome reception, and I fully understand if you're too tired from the long journey, you're not, it's not compulsory. You can stay in your hotel, take a good night's sleep. But if you're strong enough, you can come to this reception to try some Brazilian drinks, caipirinhas and things like that. They'll be available, and some local delicacies also. And again, the bus, then there'll be a bus waiting for you at the hotel just after the poster session. By 5 p.m. or so, please go back to the hotel and do not delay much. And again, for the local guys, please take your cars, because there's only 45 seats in the bus. So we will leave the bus for those who are staying in the hotel, and take your cars. Also bring your badge. To enter tonight, bring your badges, please, to this technology park. This is where they hold the spin-off companies. There are several spin-off companies in this high technology park. This is for tonight. And then tomorrow, we did this last year, was a great success. Please bring your snacks, chocolates, snacks, something from your countries, from your cities. It will be interesting, to exchange different delicacies from different countries. Even people from Brazil, you are supposed to bring, like Caliton. Did you bring some specialty? Did you bring something? Yeah. Brazilians also, bring different things from Rio Grande do Sul, from Piauí, from Amazon, from Rio de Janeiro. Let's see what we have. We have a glass orchestra. We have an orchestra where the instruments, the music instruments are made of glass. They are going to present 3 Brazilian songs tomorrow, also at the meeting. Anyway, if you have questions, let me know. Oh, very important. We are arranging for your return to São Paulo on Saturday. I think 2 shuttle buses will leave at noon to São Paulo. So if you have not given your consent to Laurie, please do so. She has to organize. Laurie, how many people have confirmed that they are going on Saturday? Laurie says that only few people have responded. So if you want to take a ride in these buses at noon to São Paulo, please send a message to Laurie. She has to organize things. Anyway, I think it's good time for a break. Let's have a break now. And then this is a short break. In the morning is a short break. By 10:15 or so, we should come back. Okay? It's downstairs. Downstairs. Thank you.
Edgar, eu mandei minha apresentação ontem à noite pro Mike. Você acha que ele tá aqui?
Se não tiver aí, põe agora. Você tem a sua? Tá aqui? A sua tá aí.
Eckert,
Você e a Rafaela
Lamar...
vão apresentar ou só ela? Agora?
Não.
Os dois? Agora também. Agora. Ah, tá bom.
Eu mandei pro Mike.
Eu coloquei aqui.
Ah, tá aqui?
Coloquei aqui. Qual que é?
Minha é na linha, Marcelo. Mandei ontem à noite, na
Tá.
verdade.
Tá com o nome do senhor?
Cara,
Ou tava outra coisa?
Será que é essa aqui? Acho que é essa aqui. Ah, tá aqui. Beleza. Ah, não, esse é do Cerveno. Eu não lembro nem o que era. Gente, vou filmar. Se eu mandei ontem à noite.
Eu mandei, eu já coloquei tudo aí. Qual que é o nome do senhor, perdão?
Marcelo na linha.
Não chegou, não veio nenhuma do Marcelo. Às vezes, será que na hora de digitar o senhor não colocou errado? Porque meu nome é com Y e K, então às vezes acontece.
O seu não tá aqui, Marcelo?
Não tá, não chegou dele. Eu tô falando, como meu nome é cheio da frescura, às vezes a pessoa na hora de digitar troca uma letra, aí o e-mail não vem. É muito comum de acontecer.
Se trocou.
Muito comum, porque é com Y e K, a pessoa lê Michael e escreve às vezes diferente.
Gigante à noite de viagem tá meio passada ainda.
Você estava no exterior?
Não, tá de São Paulo. Cara, tava tão passado que eu escrevi o e-mail, deixei aqui e não te mandei. Eu falei, mas não é possível, eu mandei.
Cansaço, né?
Eu tava trabalhando em dois computadores, acho que eu comecei a fazer uma coisa em um, outra coisa no outro e... passar vídeo. Acho que é mais fácil eu vir aqui daí, né? Dá pra, será que pra acessar
Vamos
com
testar. Tem áudio nesse vídeo?
o áudio do também.
Já testou? Esse aqui?
Não.
Esse não.
Mais pra baixo do próximo. Aí. Aqui na... Aí, na educação.
Vira aqui.
Beleza.
Vidro? É magnético? Essa eu não esperava ver. Legal.
continua? Aqui também, exatamente. Eu não tenho nenhum aluno novo. É tudo aluno velho que estão terminando, eu vou ficar sem aluno. Ricardo. Eu vou falar para ele chamar a turma. Lauri, chama a turma, bate palmas aí, chama. Ah, é sempre bom ficar no cafezinho. Hein? Very good that you, three of you came here. I really appreciate this. Very, very good. É duro chamar a turma depois do coffee break, né? Sempre. Very difficult to get people after the coffee break. É o primeiro.
Networking and everything is the most important.
Yeah, networking is very important. For networking. Good that you came. Very,
Good
very
to
good.
see you, Professor.
Very good to
Thank
see
you.
you.
Thank you for organizing this tour.
I'm really glad that the nice group from Poland came.
Thank you.
Okay, I think we have to start the next session, where the Brazilian professors are going to introduce themselves. Some of them disappeared during the coffee break, so I'm going to start with the ladies. Rafaela, I'm going to start with you because you're the only lady, Brazilian lady here among the professors. So Rafaela is a postdoctoral student, but she is so clever that she was invited to give one of the lectures. So we start with Rafaela. Tá aqui o seu?
Hello, can you hear me well? My name is Rafaela, and I'm a young scientist. I'm showing you a little bit of my professional itinerary. I have done engineering physics in the city at IFSC, and I have done my PhD straightly in applied physics. During my basics training, I got the opportunity to go abroad at some periods. I have stayed in University of Colorado Boulder, and then I have stayed for a short time in Misasa, Japan, and then I have stayed for a while in Institut Lumière Matière, Lyon, France. So in this basic training, I have worked mostly with vibrational spectroscopies, Raman, and also Brillouin. This was the title of my thesis, Correlation Between Structure and Optical Properties of Lead Metasilicate Glass Ceramics under High Hydrostatic Pressures. So during my PhD, I got the opportunity to work with this composition, lead metasilicate, and try to understand its structure under high temperature and also under high pressure. And both I have studied with the glass and also the crystalline phase formed in the system. And then when I finished my PhD, I started my postdoc in the synchrotron. I have worked in the Emma Bean line. This line is dedicated for X-ray synchrotron techniques in extreme sample experiments. Right there, I got the opportunity to work mostly with condensed matter, not just glass. And I got to learn to work with that under high pressure, high temperature, low temperature, and high magnetic fields, mostly applying X-ray spectroscopies. I loved it a lot, but I got the opportunity to rejoin the glass community. And here I am on my second postdoc, this time in this university, and this time working with nuclear magnetic resonance. This is the title of my official project, the structural role of transition metal oxides in borates and phosphate glass, studied by dipolar magnetic resonance techniques of quadrupolar nuclei. So this is the composition. We just got started a ternary system of lithium borate with some niobium. Yeah, and these are some of our results. We will be publishing this paper soon this year. I will be working very shortly with phosphates as my next project, applying molybdenum and also titanium. And yeah, this is my professional luggage so far. I have been working with multiple spectroscopies, Raman, Brilliant, X-rays, and now NMR. My formation was in silicates, but I'm working on borates right now, glass and glass ceramics. And yeah, I like extreme thermodynamic conditions, special densification, and overall crystallization. I thank you very much for the opportunity to talk in this school, and I hope to talk to you guys during this week.
Thank you. Andrea, você vem? Oh, our next speaker is Professor Andrea de Camargo. She worked for many years here in this institute. She was also a member of our CERTEV, but she moved last year to Germany. She has a position now. She is going to explain at the University of Vienna and also at BAM in Berlin. She is an expert on the optical properties of glasses. So Andrea, thank you very much for coming. She came all the way from Germany just for this school. And to see her hairdresser, her favorite hairdresser here in São Carlos also, as I heard.
That's right. Thank you very much, Edgar, for the introduction. So, good morning, everybody. It's always a pleasure to be back. And when Edgar announced that he was going to do the glass school again, I said, of course I'm coming. He asked me at least 3 times, but are you sure you can come? You know, do you confirm that you're coming? Yes, I am coming. So here I am. I would like to give you an overview of my research over these years and also introduce myself. So my name is Andrea de Camargo. I have a quite long name, but this is how I prefer to be called. I have a master's and bachelor's in chemistry from Unesp. That's another state university here in Brazil, very close to here, about 37 kilometers in Araraquara. And I hold a PhD in applied physics from this very institute here that you are attending of USP. And after a couple of postdocs, where when I was working at UFSCar and also at USP, I became an Alexander von Humboldt Fellow in Germany. So this was the first time I got in contact with the German research environment. I was in Germany for 3 years, actually working with Professor Helmut Eckert. I think he left for something. But already at that time, I was a junior professor at this institute here until 2023. So in 23, I accepted the offer from Germany to lead a glass division at the Federal Institute for Materials Research and Testing in Berlin. That's an institute funded by the Ministry of Economy and Climate Protection. And it's a joint association to the University of Vienna. Some of you might have heard of the Otto Schott Institute. That's in the east of Germany. So there I am a professor. And my research interests over these years have been property-driven research. I am very interested in optical and luminescent properties of glasses, glass ceramics, nanoparticles, hybrid materials based on sol gel chemistry, and many other materials. So during the time I was working here at IFSC, there was 17 years of contribution to this institute here. I was also able to set up a very nice laboratory for the development of optical and luminescent materials. And I have to say that this is thanks to CERTEV, our Center for Research, Technology and Education of Glasses, because most of the funding for that lab came from CERTEV. So I can really tell you that my lab here at IFSC is a CERTEV lab, although it's not in UFSCar. So the interest in the current research projects we have now is in metal doped oxide and oxyfluoride glasses. When I say metal, I mean rare earth ions. We have a very strong expertise on that, but also transition metals as scintillators and mid-infrared detectors. So scintillators are materials that can convert high-energy radiation like X-ray or gamma ray into visible light. And of course, mid-infrared detectors are very interesting for environmental applications and others. Persistent luminescent phosphors and derived phosphor in glass composites for lighting. So basically, we bring a nanocrystalline phase together with a glassy phase, and then we make composites out of this by different approaches, by using sintering or in situ growth or sol gel methodology, depending on what we want to combine. Perovskite nanocrystals and also derived phosphor in glass composites, and functionalized upconversion particles for biophotonics, biosensing, nanoheating, thermometry, etc. So I did not bring results here because I just wanted to give you an overview, but during my talk I will give you some examples of the research we do. So this is where I am based now. This is our building in BUM, Campus Adlershof in Berlin. And this is a picture of the main building of FSU Jena. A lot of what I do now has to do with administration. So when I came to BUM, I took over the projects that were already ongoing. So what we do there is to develop automated infrastructure for accelerated glass discovery. I'll tell you a little more about that. And providing expertise on thermal, mechanical, and optical properties which are introduced by me. Also at the university, I teach the course of functional materials and nanomaterials, and also solid-state spectroscopy for master students. And of course, I can advise master's and PhD students who can either work at the university or at BUM with me. So I'm basically based in Berlin, but I travel to the university to comply with my duties at least once or twice a month. For external services, I am an editor of Journal of Material Science. This is an activity I enjoy very much because it gives me a broad view of the field, so it's very nice. And also, recently I joined the editorial board of Journal of Non-Crystalline Solids, which is also a pleasure for me. And I'm also a member of the ICG TC20 Committee on Photonics and Optical Glasses. So I want to talk to you a little bit of glass digitalization. This is one of the projects I took over when I moved to BUM. As you know, glasses are ideally tailored materials, very important for many advanced technologies. But glass design is still a challenge according to specifications for a certain application, right, for a certain product. And the reason for this is actually an advantage and a disadvantage because you can make glasses pretty much out of the whole periodic table. There is a vast range of compositions you can have, but this also brings problems. Huh? And combining the properties, the very complex properties, all in one glass is an extreme challenge. And the challenge lies in the fact that we have very limited processing data available in the literature. So most of the times you try to reproduce some research that was done, and you're not able to, because the data available is not well described. And so this compromises reproducibility, of course, and another problem we have is, to a large extent, we still do glass melting by hand. And this, of course, poses a problem on safety issues, which we also need to be concerned about. So because of these challenges, we started this consortium. When I say we, as I said, I took over in 23. Was already on since 2021, with the objective to provide automated glass synthesis combined with inline sensors and tools for process optimization, and combining that with machine learning tools for property modeling, we can build a so-called ontology-based data space that provides a standardized vocabulary that can be read by machines and also by humans, and which organizes the whole data of processing, characterization, and properties in a structured way that is very favorable for the glass community. And not only that, by being able to construct this ontology, we're also able to push development in industry. So this is the main reason for this investment that was made at BUM. The so-called Glass Digital Project was developed as a consortium of the German institutions you see in the bottom there, TU Clausthal, Fraunhofer ISC, University of Vienna, and funded in the framework of a platform called Materials Digital in Germany. So here I have a video. Actually, I have two videos. I'm going to play both at the same time so you just can get an idea of the whole automation we have. So basically, we go from melting the precursor oxides, weighting the precursor oxides, melting and casting, everything in a robotic way. And we do have some nice implementations that were done during Glass Digital. For example, implementing infrared and visible cameras on top of the furnace so you can actually watch the melt, and then you can prevent overfoaming, and you can also decide when it's the best moment to do the casting, right? So this, of course, has nice implication on safety and saves time and saves energy. So this is one of the things. But this project here actually finished in July last year. And as a follow-up project, we now have Glass Agent. This one has a very strong industrial component. In fact, this project here is led by the company Schott. I think you might have heard of Schott, right? It's the largest glass industry in Germany. So the idea in Glass Agent, the motivation behind this is because, of course, Schott is interested in developing optimized glasses for new applications, such as the heads-up displays and also the touch screen displays, you know, with better mechanical properties, and also pharmaceutical packaging, optoelectronic devices. And to be able to discover new possibilities of glasses for these applications in a fast way, we have to use digitalization. So we believe this is the future, not only of glass science, but also material science in general. So that's the motivation, and of course there is a very pressing need to take into account circular economy. So what is interesting about this project here is that we are now going to introduce glass synthesis from recycled materials. Of course, the selection needs to be very specific of these recycled materials, so the glass powders, and so this is part of what we do. And finally, the idea is to develop a software agent, the so-called Glass Agent, which organizes and supports this whole automated synthesis and analysis of glasses, glass simulation in the digital twin, and including recycling in the process. So the project is funded for 5 years. It's about a 10 million euros funding, of which 1.5 goes specifically to the division that I am leading. Our specific tasks in this project here is to be able to incorporate the recycled glasses as precursor materials for the new glasses, and then we have a whole set of samples to be tested and melted according to the specifications of Schott. We will do expansion of inline characterization by installing induction furnace. I hope you can see here. Can you see before and after? So this is our robot in the middle, the yellow one. Do I have a pointer? is here. Okay. Ah, yeah, okay. So this is a scheme of the whole structure here, of the whole automated plant. You can see the robot in the middle here. This is the dosing station. So you have the different oxides and carbonates, the precursor materials. Now we are going to include a new dosing station for recycled powders of different sizes. And then the idea is to also include an induction furnace here. And the induction furnace will have a head to measure viscosity from the top of the furnace. And this viscosity head will be moved by this rail you can see on top. So basically you take the crucible out of the melting furnace, place it in the induction furnace, and then comes the head, goes in, measures viscosity, comes out, and then you know when it's the best time for doing the casting. So that's the idea here. So this is to be introduced by us. And also, we want to do measurement of composition of the glasses in the glass blocks by using LIBS spectroscopy. For those who are not familiar, LIBS means laser-induced breakdown spectroscopy. You basically use a high-power laser to give some shots to your sample, then you evaporate some material, and that is analyzed by mass spectroscopy. So the idea is to use this technique for the composition of the glass blocks. It is already quite useful for the characterization of metals, alloys, polymers, but for glasses, almost nothing is done with LIBS. And this is actually a challenge we will have to face because we will need to develop calibration curves, especially to measure light materials like boron, which is still a challenge that we face by X-ray fluorescence. Good. So I hope I gave you an overview of what we do. I would like to introduce my teams here. This is the team at BUM. We have 2 PhD students working on, one is working on hydrogen capillarity in glasses, so trying to develop glasses and composites that will serve for hydrogen storage tanks. The other one is working on developing tougher glasses, so improved mechanical properties. We also have 2 postdoc researchers, and now a very recently arrived one who also came from CERTEV, Elena. Yeah, she arrived a couple of weeks ago, so that's why she's not on the picture. And then, of course, I have some technicians and senior scientists working in the group as well. This is my team here. So I still have 3 PhD students here at USP who are working on finishing their thesis. Some of them I'm trying to bring to Germany to work with me as well. And 1 master student, Leticia, who is about to finish as well. So if you're interested to join us, we can talk about this. There are a number of possibilities of funding with different agencies in Brazil and also in Europe. And please come and talk to me if you're interested. Thank you.
Thank you, Andrea. You see how many opportunities you have been having offers to join the Alfred University team, the BUN team. Soon you get opportunities to join the São Carlos team. I wish I had such opportunities when I was a student a few years ago. You know. So, still as ladies, Anna, would you please give your talk? I'm inviting now Professor Ana Cândida. She is one of our colleagues here at CERTEV. She is an expert on the electrical properties of glass. She has been working for many, many years in this area. She was also the education coordinator of our CERTEV, our center. So she is also the chairperson of the education committee of the ICG. What's the number of your committee? TC23. There is a committee of the International Commission on Glass on Education, and she is the chair lady, chairwoman of that committee. So Anna is very much involved in education, and she is a great expert on electrical properties of glass. And also she helped me a lot in organizing this school.
Okay, good morning all. So thank you, Edgar, for this introduction. So welcome all of you. It's really a pleasure to have all of you here. And I hope it will, I'm sure it will be a very nice week for all of us. So, as I am from CERTEV, UFSCar, Lamave, so São Carlos. Just a quick introduction of my background. I have a bachelor in chemistry at the University of São Paulo in São Paulo. The University of São Paulo has several campi. I graduated in São Paulo, Brazil. Fortunately, the year is not, it's hidden. That's a chance for me. So I will not tell you how many years ago, okay? Then I may also, the year is not appearing. Oh, that's nice. So I made what a formal DEA in France. It's like a master. It does not exist anymore. And a PhD in the Institut National Polytechnique of Grenoble in France. So this was in 1988, I think. Okay? And then I came to São Carlos. To tell you quickly, when I was in Grenoble in France, I decided in my head I don't want to come back to São Paulo. It's a too big city. I want to go to a small city. Then I had the invitation from a professor, Michel Hegerter. I don't know if some of you remembers him. And I came to Institute of Physics with Michel Hegerter. And then the same year or 1 year after, I had this opportunity to do what we name here competition to get a position, to get a permanent position at UFSCar. And so I am there since 1989. And then I was hired, I must just tell in history, because I was a chemist. And materials departments wanted to have a chemist. They wanted to build a chemical analysis lab. But this chemical analysis lab was soon transformed in another thing, and I had the chance that Edgar was already there, and immediately I joined Professor Edgar initiating group. Okay? So my main research area since my PhD is the electrical and ionic conductivity of glass, So I worked since my PhD on glass as solid electrolyte. Now I work most with glass crystallization, so looking for Nasicon electrolyte. I worked also with Edgar and Ricardo and Caio on glass relaxation, some optical properties with Professor Andrea and Nilanjana, a postdoc. So those are my main topics. I will just present you some recent works. So first, on Nasicon electrolyte. I know because at least one student, Shveta, where is she? She is also working on Nasicon electrolyte. That's why I want to detail a little bit more. So I started with lithium solid electrolytes for lithium batteries. But I quickly, not quickly, then I changed to sodium batteries because the scientific community believes that lithium batteries will be replaced by sodium batteries. So this is one of, and all those Nasicon are very nice because it is a huge family. We can change the composition very much, and some of the composition may form glass. So it is also a consensus that the best method to have this Nasicon structured electrolyte is by the glass ceramic route. There are several advantages. One of them is that we can tailor crystal porosity and crystal growth and grain growth, sorry. So here we replaced germanium by aluminum, and we see that there is an increase in conductivity when we replace germanium by aluminum up to a maximum, okay? And then we see that the activation energy comes down. So that was the NAGP. It's a better glass formula, but lower ionic conductivity. We also worked with titanium and aluminum. We replaced titanium by aluminum, and there is an extra, when we replace titanium 4 to aluminum 3 plus, that is for charge balance, we may introduce one extra sodium ion, and then it increases the ionic conductivity. So we also worked in NATP glasses, and we also see that as much when we replace titanium by aluminum, the conductivity increase up to a certain limit. We also worked in substituting phosphorus 5 plus to silicon 4 plus, and the same rationale, because of charge balance, we will increase the sodium ions, and we also observed an increase in ionic conductivity. This was the NTSP system. We also did it in NAGSP system, so we replaced silicon by phosphorus, and because of charge balance, there is an increase in sodium ions, and here we claim to have found a new crystalline composition. So a new Nasicon composition including silica, silicium, and phosphorus. So, but this is on the paper. So then here it is a very interesting paper with Heinrich Brattmüller and Helmut Ecker, where we studied the isothermal evolution of Nasicon systems. So we took one composition and we studied it as a function of time. And we saw that the Nasicon may decompose during time, with time. But surprisingly, this decomposition does not change a lot the ionic conductivity, which is here. Oh, sorry, this is in the beginning. It keeps increasing, the ionic conductivity. Although we have the main phase, Nasicon phase, decreases with time, okay? But I can discuss it later if you wish. This is electrochemical stability, so this is coming back to lithium, and thanks to Vinicius, who is here, we studied the electrochemical stability of Nasicon of LAGP solid electrolyte. So this is very important because for a solid electrolyte, it must not only have high ionic conductivity. It is crucial that it also have some good electrochemical stability, otherwise the electrolyte will decompose when you in contact with lithium and cathode. So we found that electrochemical stability window was around 3.5, while the predicted value is much lower. And we explained that because the kinetics of reaction of this electrolyte is very slow, very sluggish. That's why experimentally we have a broader electrochemical window. So then I moved back, still with solid electrolyte and Nasicon. We applied, thanks to João Vitor Campos, which introduced at Lamav the flash sintering technique method. So we started doing the same Nasicon, but now with flash sintering, doing flash sintering. I will not explain here what is. So it is a crystallization which is, we crystallize the glass under electrical field. So electrical field assisted crystallization. The flash sintering is very well known in ceramics. They sinter zirconia. It's very well known by flash sintering. But we were the first one which made flash sinter crystallization. We have a patent with Eduardo, but we were the first one to crystallize glass under electrical field. So we have two papers of this. We're working on the LAGP, now on the LATP. And so we found on the LATP that when we have the composition with flash sinter, it's a little bit higher than when we do a classical crystallization. And so then another paper with flash sintering, we applied here the power hump flash crystallization. So this power hump, the flash sinter, we may control either the current, either the tension, the applied tension. But here we made the power. So the U versus I, we controlled the power hump flash crystallization. This was also very new. Not very, this was totally new, and it was applied to a dental glass, lithium disilicate, and we see we could have several colors on this lithium disilicate just by changing the power amp. And this is very important for dental because dental always looks for different colors to be applied. Okay, and coming back a little bit to basic science, I must say I am very much basic science driven. I like also very much this kind of subject. So with Professor Jean-Louis Souquet, Márcio will be here this afternoon. I like very much this paper, so we could, Caio already talked about, we could separate the effective charge carrier numbers from the mobility just by calculating the enthalpy of formation below and above TG. So below TG we have an Arrhenius expression, and above TG it's a VTF expression. So there is a change here, and we can, by doing calculation, we can separate N, which is the effective charge carrier concentration, not the total alkali concentration, from the mobility. This is another paper with Caio. It was also a very nice paper, in which Caio, in his PhD thesis, Caio Bragato, he experimentally measured the activity of Ag silver iodate on this very famous glass, silver iodate, silver phosphate glass. And we found that he measured doing a battery, very interesting. He can talk to you if you want. And he measured that the conductivity is proportional to this log of activity. And this joins the weak electrolyte approach from Jean-Louis, from Professor Souquet. This is very much basic science, theoretically. So, and now this is my newest article, last one, also with help of Vinicius. We measured by measuring the interfacial capacitance in a lithium disilicate glass, we also could calculate the N, the effective charge carrier density, and separate from the mobility. So this is, the idea is that the interfacial capacitance in the electrode, when you take the electrode, the capacitance is proportional to N. Speed up. Okay, thank you, Edgar. So this is the final article, and here we could calculate our effective charge carrier, my acknowledgement while I have, and those are my former students. I hope I did not forget anyone, and I must express many, many thanks, not to our students, but to my colleagues, Edgar and Professor Oscar from LAMAV, which takes LAMAV, the infrastructures, and brings LAMAV to this high top level. Thank you very much. Sorry, Edgar, if I passed some.
She always gets very excited with the research. We all do. But this this is not the tutorial yet. This is just an introduction, so I will ask my colleagues to keep it short. Keep it short. It's just a brief introduction. Now we come to the male professors. Starting by seniority, I invite Professor Helmut Eckert, my colleague and vice director, to briefly present his research interests. Please, Helmut.
Get to this?
Did you send it to?
Yeah,
Huh?
I sent it.
Max, acha para ele.
Acha pra mim. Okay. Yes, my promise to you, it's going to be brief. I will talk about general things, and Marcus will follow my presentation and show some concrete results. So we split the responsibility here. Here you can see what I list on my curriculum vitae as background. I was a professor in the United States in Santa Barbara, then at the University of Münster, and now at IFSC since 2011. And yeah, our main agenda is to find new methodology of solid-state NMR and apply it to disordered materials. In particularly, the glassy state is at the heart of our interest, and so we are, of course, very happy to be part of the ZTEF effort. So basically, the periodic table offers practically for every element, with the exception of argon and cerium, an isotope that can be used for NMR spectroscopy. And all the ones that you see in red lend themselves to essentially routine applications using standard methodology. Sometimes the isotopic abundance is very low, although the isotopes are important. These are shown in yellow. And then we need isotope enrichment. The ones in purple and blue are currently at the heart of our agenda. These are quadrupolar nuclei, in which the nucleus is not spherical, but actually more ellipsoidal. And this particular nuclear shape affects the NMR spectra in a very profound way. It makes lines extremely broad, and therefore these nuclei normally escape standard methodology. And currently this is a focus in our laboratory to develop the possibilities we have there. In particular, where's the... Right now we are interested a lot in niobium. Niobium, of course, is important for Brazil because of the monopoly. And niobium in glasses is a hot area right now to impart to them special optical properties. And niobium is also, in principle, a very excellent NMR nucleus with excellent detection sensitivity. But the problem is the quadrupole moment. And right now we are developing methodology to make this nucleus available to learn more about niobium in glasses. And basically the momentary results is niobium can be treated like a network former, not a network modifier. Okay. And the ones in purple are the ones that have a moderately sized quadrupole moment. The ones in blue are even more challenging and may require even further effort. Anyway, so this I will go through very quickly. Basically, in NMR, we exploit internal interactions that nuclei feel, aside from the external magnetic field, from internal magnetic and electrical fields that reveal parameters. Oops. Oops, no. Back. De novo. Okay. So that reveal reveal interaction parameters that how do we here, ne? Yeah. Thanks. That teach us about chemical bonding and chemical bonding and internuclear distances. In particular, the focus in our lab is the quantitative interpretation of magnetic dipole interactions. So basically, to probe the proximity between nuclei of the same kind, homonuclear interactions, or nuclei of different kinds, heteronuclear interaction. Okay, here's our overview of our equipment. We have 4 spectrometers available to us. One of them is actually a multi-user equipment available to IFSC in general. And you can see we can spin very quickly, depending on which field we are at. And I want to also state that in addition, we have access to EPR spectroscopy through collaboration with Professor Magong. And yeah, this is the people. So here, Jose Schneider, who is the director of the 400 megahertz facility, Marcos and Henrik. Henrik recently hired at IFSC as a new professor, and Claudio Magong recently retired from IFSC, but he is running the EPR, the electron paramagnetic resonance effort. And then I'd like to list all the collaborators that we regularly interact with and regularly publish with. Some of them are here. Andrea is here, Magong is here, and I'd like to also highlight the contributions of Professor Phil Sarman, who will be visiting CERTEF next month. Okay, so with this, and thanks to all the funding agencies, and a picture of the group uniting now the joint groups of myself, Marcus, Henrik, and Jose Schneider, I'd like to end and thank you for your attention.
No, it's very good. Thank you very much. I forgotten to introduce Professor Helmut, but if you did NMR work in glass, you have seen his papers, for sure. Over 500 papers in this area, so that's enough. Following up this seniority strategy, I think I'll invite now another guy with white hair, Professor Pisani, who, you know, Professor Pisani is very famous at our university because he got an award for working 50 years, right? 50 years at the Federal University of São Carlos continuously. There's only maybe 2 or 3 guys in the whole university that worked for 50 years. I only worked for 48 years, so not good enough yet. He is a great expert on Raman spectroscopy, as you're going to see. But please, Pisani, just a short introduction. You have a lecture, you know. You have a lecture tomorrow.
Who is my talk? Good morning, all. My mini CV, it turns the micro CV, maybe nano CV, my presentation, okay? My professional definition is I am a physicist, researcher, professor at IFSC since 1974. Passionate about the challenge of understanding the behavior of nature and the genesis of the materials and their correlation with properties. So defines exactly my definition of a professional. Born in São Carlos in 1950. My academic formation, graduated in physics in 1972. Unesp Rio Claro is a city near here. Master in 1977. Nuclear magnetic resonance in liquids here in São Carlos. PhD in 1981. Electron paramagnetic resonance in color centers in aluminosilicates here too. And the postdoc in 1994 on Raman spectroscopy of 3-5 semiconducting actor structures. My scientific production is 270 papers, 8,000 citations, H-index 51. Research interests, crystalline glass and glass ceramic materials, in situ pressure and temperature effects on vibrational spectrum, mainly on Raman spectrum. It's all. Thank you very much.
If some of you work on Raman spectroscopy and like to see his lab tomorrow, you'll be there, Pisani, tomorrow in the afternoon. You'll be available tomorrow in the afternoon? Yeah? So if somebody wants to visit your lab, you'll be around in the afternoon. Because they are going to La Mave in the afternoon. Anyway, if some of you is interested, tomorrow you can escape as walking distance from my lab to his lab to see. He has a very, very nice... Yeah, but the equipment is very good. And the head's also very good. The minds are very good. Okay, so following up this tradition, I come to Professor Pedro Rino. He says that he retired after 49 years and 9 months, 8 months, something like that. So you are his senior.
Okay, everybody. I'm a senior professor at Physics Department, Universidade Federal de São Carlos. My background, I got my degree there in UFSC, Universidade Federal de São Carlos. My master degree here, I was studying confinement effects in magnetized boson gas. I'm not sure, but I was one of the first person in Brazil who studied Bose-Einstein condensation theoretically using this guy back in 1974, something like that. PhD, here with studying correlation in simple liquids. Then I started my postdoc at Argonne National Laboratory. I spent 2 years there. Then I spent some time in Louisiana State University and University of Southern California. I learned molecular dynamics simulation at Argonne with one of the founders of molecular dynamics. This is pre-fascista. Which one is that here? Esse aqui? O de cima. This is the pre-fascista. He's the boss of this group at LSU. We are having some fun in Taiwan. This is the visit of Richard Smalley at LSU to visit his group just before Smaller got the Nobel Prize, right? Nobel Prize in the buckyball discovery, that stuff. Yeah. What make my life happy, I like, scientifically speaking, is to develop interatomic potential. And I have been developing for several systems: silica glass, densified physical glass, silicon nitride, alumina, and almost all the semiconductors, 2635 semiconductors. Several oxides, vitreous lead silicate, vitreous barium silicate, and at this moment we are studying magnesium silicate. The idea is to always in collaboration with experimental group. We can, using this potential, we can study crystal growth in supercooled liquid, and we can study spontaneous crystallization, and we can test theoretical models. So what gives me really excite me is to develop potential in general. It's not easy. It's very complicated. The people who knows molecular dynamics, what I can say is that I always try to find out one potential which describes not only the structure of the material, but also other properties, like mechanical properties, like dynamical properties, and so on. So the potential in general are very reliable to do that. And that's it. I hope I can make another potential. It's not easy, it takes time, but works fine. Thanks.
Okay, now I come to the young guys of the group. They are sitting here. I think you were the first, right, Edu? You know, he's a young guy because he was one of my students, so a very young guy. Eduardo Ferreira, he is an engineer. He did his undergrad and graduate studies in materials engineering, and he likes to do a lot of glass recycling, sintering, crystallization, chemical durability, you name it. Anything with the keyword glass, he'll be interested.
Thank you, Edgar, and thank you all, and welcome to São Carlos, and it's a pleasure to receive you here and be part of this school. Well, I'm Eduardo, and now I'm an associate professor at São Carlos School of Engineering. It's part of IFSC, University of São Paulo. I'm located in the, let me find here, Materials Engineering Department. Just to say a few words about our university, this is the largest university in Brazil. We have huge numbers, 183 undergrad courses, 239 postgraduate courses, 58,000 undergrad students, 30,000 postgraduate students, and so on. We are more or less 20% of all Brazilian scientific production in all areas of knowledge. Well, I'm sorry. We have in this university 42 teaching and research units. 5 of those units are here in São Carlos: architecture, physics, chemistry, mathematics, and computation, and engineering. So São Carlos School of Engineering is one of those units. And then we have some departments and some centers. We are in one of those departments, Materials Engineering Department. And this is to give you a view. You are in São Carlos now, okay? You're here at USP downtown. Federal University is, how do I do that? Okay, here outside the city, and the new area of São Paulo University is also a little bit outside the city. Our department, this is downtown University of São Paulo. We are now here in one of these buildings here, and this is the university, but it was not so large enough to grow, and then we had to move to another area, and this is the new area of the University of São Paulo, and our department is here, the Materials Engineering Department. You have a chance to visit us on Saturday if you like, okay? Well, this is our department, and some highlights now about what we are doing there. Before, this is my background. I was graduated in materials engineering at IFSC. Started more or less here 2 years after to work with Professor Zanotto. And then, since then, we are working together. I've been working with him since I was a small baby. Yes, and then my master was, again, together with Zanotto on residual stresses in diopside glasses, crystallized on the surface. And then the PhD was using, still making slag to produce glass ceramics. And the postdoc was recycling soda lime glass to produce sintered glass ceramics for tiles. And then after I became a professor at Unesp, but in Guaratinguetá, not here in Araraquara. And since 2010, I'm a professor here at this university. And since 2013, I'm working together with CERTEV people. I've been working with materials engineering, but especially on glass and glass ceramics. And I'm interested in glass forming, glass sintering with concurrent crystallization, glass ceramic manufacturing from the powder technology, or using the powder technology. Glass ceramics development for several applications, glass recycling, and mineral waste is recycling into glass and glass ceramics. Well, this is a list of masters and PhD projects. I won't take your time on this. If you are interested, we can talk more. But some of my research lines, the current research lines, those that I'm more interested nowadays, we are working with 3D printing of glasses using traditional polymer printer and dissolving or suspending the glass powder in the resin. And this is performed now by Ana Caroline, that's here. She is going to give you a far talk about this and has a poster on this if you're more interested. And we are working with glass fertilizers for controlled nutrient release. If you see the nutrients necessary for plants are very much those that we can find in traditional glasses, and then it's kind of easy to produce a glass for with that composition, and not so easy, but that's what we're interested in, is how to control the solution rate to give to the plants what they need. Another important research line we are working nowadays is using some mineral wastes to produce artificial rocks for building, and that this was obtained by sintering the glass powder. If you care, if you pay attention here, you can see some reflection. And finally, we are also working with flash sintering of glass like Ana Candida. Okay, and that's all for a while. And if you would like to talk with me, you can.
Thank you. Thank you very much, Eduardo. Now I am inviting Marcelo Nalim. He is an expert on the optical properties of glass. He formerly worked at the Federal University of São Carlos. Then he decided to move to a university which is only 30 kilometers here. So it's still in our backyard. So we let him stay at the CERTEV. And luckily I did that because he is doing a lot of interesting work. So Marcelo, thanks.
Thank you, Edgar, for the introduction. Good morning, everyone, and really welcome. Be welcome to São Carlos and the school. I will just give you a brief introduction about what we are doing also in Araraquara. It's, as Edgar said, it's just 30 kilometers far from here. We are a quite old group. In fact, I started my PhD, my master degree there. I'm chemistry, and my formation is basic formation is in chemistry. I start my master in glass materials, work on optical properties of glass materials in Araraquara, and did also my PhD there. During the PhD, I have the opportunity to travel a little bit. So I spent 1.5 years in France, in Université de Rennes. I work also on glasses. And I have the opportunity to visit Professor Helmut Eckert in 2000 in Münster, in Germany. And then I also spent another year in France, in synchrotron studies using EXAFs and exams measurements in absorption, X-ray absorption, studying the structure of glasses. And then back to Brazil, and I give a position in the physics department, not a position, a PhD position, postdoc position in the physics department at University of Unicamp. It's another state university here in São Paulo. It's around 150 kilometers far from here. And during this time, using my background in glass, using a lot of physics, studying holography in glasses. And then 2009, I joined the chemistry department here in UFSCar, when I have the opportunity to be more in contact with Professor Edgar, and then he invited me to become part of the CERTEV group. But just some months later, when the project was accepted, there was the opportunity to join my old group in Araraquara. So I just back to Araraquara, but we continued working together, and it was a very proliferous period of my career. So just give an introduction. This is our main group in Araraquara. Professor Sidney, was my co-advisor in my PhD. Professor Yunis Mesadek, maybe some of you have already listened about him. He's now in Canada, but he's continued to be a member of our group in Araraquara, but he's now in Quebec, in Canada. So we still work a lot together. Silvia is an expert in NMR, and Douglas Franco is also works on optical glass. He's joined us 2 years ago, and so the new one. And just in January, we have another guy that joined us, Elias. He's a former student here from USP, also a chemistry one, but work not in glass science, more in soil gel and other materials. So Araraquara is here in the middle of the state of São Paulo. We are pretty close. São Carlos is just here. This is our campus. It's very easy to reach the university because it's on the road. If you come from São Paulo, you arrive in São Carlos by Washington Luiz Road, and if you continue 30 more kilometers, you will reach our university here. So our department is just here too. This is the entrance of the university. We are known as House of the Sun, or Arara Hell, because it's quite hot city. So this week it's okay. It was supposed to be around 34 degrees or 35. I expected it to decrease a little bit because it's really quite tough these last days. So, but we have very nice pictures from there. So this is Araraquara. So concerning the research lines we studying there. So as I told you, I start to work on optical glass, mainly based on oxide glass. So we work with a series of glass, but mainly glass for nonlinear optics that based on heavy metal oxide glass. We have already also worked with some chalcogenide glass in the past, but we prefer to move because just with the oxide glass, because it was we have a very nice cooperation with people from Rennes University that are really, really very specialists in this field. So we can exchange experience and samples with them. So we just focus on the heavy metal oxide glass. We have a facility to pull optical fibers in Araraquara. I think this is the only optical fiber tower in the South America, and that allow us to draw silica fibers, but we also work mainly in soft glasses, oxide soft glass. Okay, so we are also interested in many luminescence properties of glass and crystals. One of the main fields that I'm working now is related to magnetic glasses. So, as most of you know, glass are known because they are not interactive with magnetic field, not so much. But in fact, what we are doing now is change the composition and make this glass interact with the magnetic field. I will show you some results later. So the luminescence, so in glass and crystals. Also, we are interested in greenhouse gas sensors obtained by using the crystals or even glasses. And so I just moved here show some of the magneto-optical properties we are studying. So we are able to prepare glass materials, ceramics, optical fibers. It's not silica-based optical fibers, it's heavy metal oxide-based optical fibers, usually contain a lot of Hertz elements inside, and for those that has already worked on trying to put Hertz inside glass, this is the challenger, because usually when you increase the amount of Hertz, it tends to crystallize, and in this case, we don't want any crystals inside the glass. But I show you that sometimes life is interesting, and in glass science too, so we have some other results concerning this. So hybrid materials where we mixed glass and nanopowders, nanomaterials, nanoparticles, magnetic nanoparticles. So we synthesize magnetic nanoparticles and then we mix it with glass to make a hybrid glass, okay? Thin films and also crystals, okay? So this is the main applications for this magneto-optical glasses. It's optical fibers. We can go in two directions. We can have glass with are very sensitive, so to very low magnetic field, but we can also apply this glass to monitorize as sensors for high magnetic fields. So we are working on both directions. This is just one small video about a magnetic glass. Okay, so this one is completely amorphous. It's just a paramagnetic effect. So when you charge the glass with a very high amount of Hertz, so we can have this kind of sample. So we use them as Faraday rotators. We can prepare sensors like this one from magnetic fields, bare optical fibers. This is some just examples of fibers, and now we are working on obtaining single mode fibers using this glass. This is a huge task for those that has already worked with the optical fibers. For silica, it's a piece of cake. It's really, really easy today. But for when you work with a very complex compositions, it's not easy. It's not easy at all. So in the last just 2 slides, I would like to introduce you we have been working with this kind of glass containing Hertz, and I cannot say that it was for an accident, because we are working for glasses. But for some reason, we find some very nice crystals. And what we are doing now, we have a heavy metal oxide composition that when you put Hertz inside, depending on the amount of the Hertz, it separates phase. There is a separation of phase that happens at high temperature, and we can obtain very nice crystals like this one. And this is just an example. This is one crystal. The main composition is gallium garnet. It has 4 Hertz on the composition. Here is thulium, erbium, ytterbium, and yttrium. It is a false Hertz, but 4 Hertz on the composition. And this is the kind of crystals we obtain just cooling the glass. And when the phase separation happens, we obtain this kind of cubic crystals, completely monodispersed inside the glass, and then we can dissolve the glass and just have the crystals. And one of the most interesting in this research is it doesn't matter what the ratio between the Hertz you put in the glass, we will find this ratio inside the crystals. So we can obtain, doesn't matter how many different compositions of crystals. So this is one of the results. This is for white light generation. This is using up conversion. We are going to talk about this. Probably Andrea also will talk about this in Wednesday. So we have exciting the glass on the infrared. We have white light emission, and we can modulate these emissions by changing the ratio of the hertz. And just to finish, this is something very problematic, but not so many people talk about. This is the silhouette, in fact, unfortunately, of a bird on a window. Okay? You can see here the wings and the head of the bird. So, unfortunately, it died, and now we are trying to move on some technology to avoid this. Why it happens? In fact, for us, for humans, we can see sometimes the reflection in a transparent glass, but sometimes you cannot see even. We can hit with the glass with our face, okay? And birds is the same. But why it happens is because birds have they see the world completely, just a little bit more different than us. We have our main vision point here in the visible, in the green light, the green color. But the birds, they see in 4 dimensions, and they see in UV. The most sensitive wavelength for birds is in the UV. So what we are doing now is trying to develop some coatings that can be applied on the glass surface in a very large scale, okay? So here we can see some the coating on the surface of a glass, and when you apply the UV light, you see the black stripes, okay? So this means this glass can be black for birds in UV, so in this direction he could eventually see some glass in front of him. And it's not a problem for architecture, because usually humans don't see in this wavelength. So this is something that we are looking for now. So just I would like to acknowledge again our research group in Araraquara, and also the CERTEV group. This was an amazing journey to be here for all these years, for my scientific career, for all the people that I met in this time. So I would like to thank you again. If someone has some questions or something where we can discuss later, please contact me, and I'll be here some days during the week and to discuss with you. Thank you very much.
Yeah, we still have 3 people to talk, and I'm inviting now Professor Francisco Cervena. He is not officially a member of CERTEV. He works in another state. The CERTEV is funded by the state of São Paulo, so we can only directly fund people who work in the state of São Paulo, but he has been such a wonderful collaborator for many years that he is like an honorary member of the CERTEV, and he is always collaborating with us, and a great expert on the mechanical properties of glasses and glass ceramics. So thank you very much, Francisco, for coming. He has some fractured bones currently, and even though he decided to come, and he drove like 500 kilometers or so. 500, how many kilometers? 500 kilometers from his hometown in Paraná to São Carlos. So thank you so much, Francisco.
Thank you very much for the kind words, Edgar, and for the CERTEV for the invitation. So I am... So my interest is on mechanical properties of glass ceramics. And just to show you where we are. We are in the south of Brazil, Ponta Grossa, and here we are just to show you more or less about 500 kilometers southwest, and here is São Paulo, São Carlos. Here is from where I am. Edgar asked me to be brief because we are on time. So what I like most, if I look back at my works and my interaction with Edgar, since I did a postdoc here, I was already a professor. I did a kind of sabbatical with Edgar in 2005, 2006, and then we started collaborating. But I'm always trying to test models on mechanical properties in glass ceramics in order to try to understand what are the mechanisms and what are the fundamentals of the mechanical behavior. And as such, we like to work with model materials. One of those is lithium disilicate, and the other is barium disilicate. But how I'm also interested in residual stress in glass ceramics, wear and tribology, brittle ductile transition, bioglass ceramics, sealants. Recently, with Ronnie, we have some work on, and some other here's alkali niobium phosphate glass ceramics, and also transparent glass ceramics. Lithium disilicate is a model material, model glass ceramics, because it's a stoichiometric, the chemistry between the glass and the crystal. And one important thing is it has huge technological application in dental materials and has compressive residual stresses. Barium disilicate as well, it has tensile thermal residual stress and has several optical applications. This is some works that we have published during the years. We started this with, we measured several mechanical properties. This was Ivan, which was one of my PhD PhD student, and we did some very nice measurements on variation of K1C and bending strength of crystalline volume fraction. This is a collaboration with Mariana Villas-Boas, who was a PhD student of Edgar, and essentially she changed the residual, the thermal expansion of the residual glass, so we could study the effect of the residual stress on the residual glass on the mechanical properties, and we found that it has no effect, at least for the conditions that we measured. We also did some collaborative study with some Dr. Viviane Soares, which was a PhD and postdoc student of Edgar. And this work is a new dental glass ceramic, which has a house of cards structure, which has a very high fracture toughness based on silicate glass, lithium silicate glass, and has a very high fracture strength and fracture toughness. So in compare with other materials, it has a very high, good, very excellent mechanical properties. This is another material that we work in, transparent nano lithium disilicate. It has nanocrystals, and what we learned from that is that you can improve mechanical strength, but not fracture toughness. This is one of my PhD students, Simone, and she studied the variation of crystal size on fracture toughness and other mechanical properties, hardness, elastic modules. We did a complete study here. We showed that it presents R-curve behavior. We have some interesting behavior here related to strength variation with microfracture of the structure. This is another student of mine, Marisa. She did a very nice work on varying crystal size and crystallized volume fraction on lithium disilicate. And then we correlate what we observe here, the microstructure, with the variation of fracture strength and toughness with crystallized volume fractions. These are only the experimental results, but we have some models that we apply on that. We are the first to apply models of micromechanical work on fracture toughness modeling on glass ceramics. This is some current work on R-curve behavior in collaboration with Renan, and Ronnie is here. He is a PhD student. We are doing some, how the R-curve behavior that we observe in glass ceramics is related with crystal size, with microfracture that we see in the microstructure for crystals above a certain type. So what is related to that is not easy to measure. You see, this is the only known curve for R-curve behavior, but this is related for dental glass ceramics, which is off stoichiometric. So we are trying to measure in stoichiometric glass ceramics. And also, this is another master project. Rafael is here, so she is trying to correlate the mechanical strength and fracture toughness of biosilicate, which is a glass ceramic, how it varies with crystal size and crystallized volume fraction. This is the work that, this is the people that we have worked with during these years, and thank you.
Thank you very much, Francisco. Marcos, I'm calling Marcos. He is a member of the faculty here in this institute, also working at Helmut Eckert's group on NMR. Marcos was a student for Helmut, I believe. Você foi estudante dele, né? Postdoc. He was a postdoc, and he is now a professor here at USP, also an expert on NMR. So thanks, Marcos. And he helped us in organizing all the logistics here of this theater, of the poster section, etc., etc. So thank you very much for helping the organization, Marcos.
Okay, thank you very much. So as Edgar said, I'm a professor here at IFSC since the end of 2019. So my first semester teaching here was during COVID times. So my first experience teaching was online teaching. So I would go through a timeline so you can have an idea of my career. And then from this, you are going to get the perspective of why I'm working with now. So I started my PhD with Professor José Schneider, that's also a member of CERTEV. And we were working with these hybrid materials. So it's a silica matrix, and it's very hard to work with this. It's a silica matrix, and it's a siloxane matrix with organic groups attached. So we dope this with these chromophoric dyes here. So when we irradiate these samples here with UV light, they change color because the tungsten here, they have an electron that's promoted, and then we have DD transitions, and this gives this black color, this absorption in visible light. But the idea here was to characterize these samples through NMR. So NMR is a very selective technique. Helmut started explaining a little bit about this. And we can always look to each nuclei, each species at a time, and we can have a local information about the coordination environment of these species. So for this kind of sample, we can, for example, run silicon NMR to study how the silica matrix is condensating. And then we can use carbon NMR to study how these organic groups are attached to the silica matrix. We can use proton NMR to study hydration environments in these samples. And phosphorus NMR, phosphorus right in the middle of this spheric molecule here. And then we can use phosphorus NMR to study the local environment of this polyanion that's responsible for the photochromic effect. And we are also, when we radiated samples, we have an electron, unpaired electron here, so the tungsten is in the D5 configuration. And then we can could use EPR to characterize this irradiated state. Then after, with Helmut, I did a postdoc with him here at IFSC also. And we were studying glasses for photonic applications. So just parentheses here, these were not glasses, but they were amorphous. So for NMR, it's the same thing. We studied the same way. And these were glasses doped with rare earths. So they were luminescent glasses. So the idea here is that we were mixing phosphates with fluorides to obtain a nice glass matrix. So phosphates give good quality for the glass, while fluorides, they have good optical properties. So we were trying to put both properties together. To do this in a nice way, we need to have the rare earths in fluoride environments. So the idea here was to study these systems and see where these rare earths were sitting. So using NMR, for phosphorus and aluminum NMR, we could study the structure of the aluminum phosphate network. And then from EPR, especially post-EPR, we could study the coordination environment of the rare earths themselves. And by using luminescent emission of europium, we could correlate the properties that we were observing from NMR and EPR with properties that we were observing for the luminescence itself. And then during my period here with Helmut, I had a short stay at Switzerland in ETH with Professor Gunnar Jeschke. Gunnar Jeschke is a professor that specialized in post-EPR, so he's the guy who, together with Schweiger, they wrote the book, main book we used to study post-EPR. So there, I went there mostly to learn EPR. Then to do this, we decided to study these systems where you have this nice molecule here. It's highly reactive. So I was studying an adduct of this with nitroxides incorporated. And then from EPR, we could look to this electron and how these nuclei around are affecting the signal of the electron. So by doing both continuous wave, post-EPR in different frequencies, we could get a scenario of what's happening in this molecule and compare with NMR results from this diamagnetic species here. So after finishing my postdoc with Helmut, I went to Germany, in Darmstadt. Darmstadt is a city close to Frankfurt. And there I was working with another technique that's called the dynamic nuclear polarization. So dynamic nuclear polarization puts together the advantages of electron resonance and nuclear magnetic resonance. So in this technique, we take the polarization of electrons that are 3 orders of magnitude higher than the nuclear signal, the nuclear polarization. Then we transfer polarization from the electrons to the nuclei, and then we observe the nuclei doing the normal NMR that we are already used to do. And by doing this, we can study special systems like bigger organic molecules where you can attach paramagnetic labels in these molecules. Porous materials, because we can incorporate the radicals inside the pores. So here are 2 examples, mesoporosilica and the metal-organic frameworks. And this work with metal-organic frameworks gave me the ideas for the work I'm running now. That's puts together more or less what I was doing in the PhD. That was working with hybrid materials, organic and inorganic materials. And my work with glasses with Professor Helmut. Then nowadays I'm working with organic and inorganic glasses that are obtained from metal-organic frameworks. So the metal-organic frameworks are usually crystalline materials where you have nice organization between metal nodes and organic linkers. So this makes this material, forms a 3D framework, highly porous. And recently it has shown that these guys here, they can form glasses. So they have a nice glass transition. They have a high glass forming ability that my students will show after. And we can take advantage of this porosity and all the advantages we have in the fields of metal-organic frameworks and apply this to the glass state that brings other advantages, like we can work in the shape and etc. And here are some of our results. So the results with ZIF62, that's a metal-organic framework with zinc, imidazole, and benzene imidazole. These two molecules are represented here. We are replacing zinc with cadmium. And the idea was to study cadmium with NMR because it has much better properties than zinc to be studied by NMR. It's more sensitive and it doesn't have the quadrupolar coupling that zinc has. But in the end, we found out a nice system where you see the normal systems in the literature, they never see recrystallization of these systems. And here we could see a glass transition and a recrystallization of the system. So after observing this phenomena, we started investigating more deeply these systems and how the cadmium defects are created, and etc. So as a summary here, in this field, we are most worried about glass formation, which compositions would form a glass, which ones would not. We are characterizing the short and mid-range structure, and we are also interested in making composites of these glasses because they have very low TG, very low melting points, so we can have composites with nanoparticles that would be destroyed for normal melting in oxide glasses, for example. So this is our group here, and thank you very much.
Thank you, Marcus. Marcus. Okay, since I'm the school chairman, I can have a few minutes more, right? As I said before, this is actually the fourth school. I have organized one of these schools long ago, in 2010. We had one school, but that was on material science in general. So this is the third glass science and technology school, but we had one years ago on material science. In all of them, we had about, we had 100 people in the first one, 110 in the second one, 75 last year, and I think we have about 75 students, and summing up with the professors, 95 people or so. So they're all the same size and the good size. I think in Wuhan, you had about the same size, right? More or less the same size. So these are very, very successful schools. And as I said before, they also hold similar schools in Montpellier in June or July. And again, in Kolkata, they had this year in January. And another one in November in Wuhan, right? In November, we have another one in Wuhan. Tomorrow, we are going to get a group photo like this one. This is our lab, so we have one tomorrow. Please come to our lab tomorrow. Let me tell you a little bit about my history here. I started in 1976. I was an undergrad student in 1976. And we had this American professor, O.J. Whitmore. Professor Whitmore, this man here, he was retired from the University of Washington in Seattle, and he came here to spend a sabbatical year because our department was starting and had not many professors. So luckily, he was working on nuclear waste disposal glasses. He had a grant from the Pacific Northwest Labs. And he brought some glass samples with 25 components in it, and he wanted to study the chemical durability. Guess what? I was the internship student who worked for him for a year, trying to learn a little bit about glass. That's how I became interested in glasses in my final undergrad materials engineering year. Then I did my master's here with Professor Aldo Krajewicz, who unfortunately passed away last year, in using small angle X-ray scattering on phase-separated glasses, trying to work on nanostructured glasses even before nobody was talking about nanostructured glasses. Professor Krajewicz was doing that in 1970 or so, using small angle X-ray scattering. And then, that's my connection with Alfred University. Have you heard of this book here called Modern Glass Practice? Alfred, guys? This book was written by a famous professor in Alfred, Professor Scholes, Samuel Scholes. And the 7th edition was enlarged by Professor Charles Green. Guess what? Professor Charles Green came to this institute as a visiting professor. He was retired from Alfred in 1977. So he came here in 1978. And this is Professor Charles Green. And he taught the very first glass course in Brazil based on this book. So he brought his own copy, and he let us to make a Xerox. This is Xerox copy with, the consent of Professor Green. And this was our first glass course in Brazil. So this is my connection with Alfred. Please pass on. And this group is still in our library. And then Marcos kindly found it in the library. So I studied this book many years ago. And that's, my connection with Alfred. Alfred, those days, was the very best. There were 2 top schools in the world for glass. Sheffield University and Alfred University. For different reasons, I ended up doing my PhD at Sheffield University. And I tell you how, why I went to Sheffield University. Because Aldo Krajewicz were good friends with a professor called Peter James. And I was accepted by Peter James. Just, Aldo sent a letter to Peter James, and I was immediately accepted. No exams, no TOEFL, nothing. I was accepted. That's why I went to Sheffield. It was very easy. And went to Sheffield, and that's where I did my PhD in glass technology. I don't think they still have a PhD in glass technology. The whole department disappeared, But luckily, Alfred kept, their department of ceramics and glasses, and we see 6 faculty here. And that's why I made a big effort to bring you guys here. It's a dedicated department to glass science and technology. And I know that Professor Ji Hong also have a huge department of glass science and technology in Wuhan. And the other ones in France, in Rennes. We have 1 guy from Rennes here. 2 guys. Big groups. Glass science and technology in Rennes, the mechanical properties and the chalcogenide glass groups in Rennes. So, and the 4th one is here in São Carlos, our research lab. So these are some history for you guys to remember about the glass research. 3 faculty members retired, Charles Green. So Charles Green, he worked for Corning for several years. He worked a lot on improving and developing Pyrex glass and this type of glasses at Corning, which are very important those days. Low thermal expansion, high chemical durability type of glasses. Then he went to Alfred from 1953 to 1969, and then he came here in 77. Actually, he came to my wedding. He was invited to my wedding, and he gave me a gift. It was a $20 bill. It was his wedding gift, which was some money those days, you know. It was not negligible in 1979 when I got married. Okay, so this is a little bit of history, and then I'm going to talk a little bit about our laboratories, LAMAV, the Vitreous Materials Laboratory. Vitreous Materials Laboratory, em português, é Laboratório de Materiais Vítreos. Laboratório de Materiais Vítreos. Vitreous Materials Lab in English. We started this lab in 1977. I started it in 1977. And these are photos of our lab. And in 2013, we had this very generous funding from FAPESP, the state funding agent, to start the CERTEV, the Center for Research, Technology, Education, Vitreous Materials. And this is a combination of faculty from the chemistry, physics, and materials engineering department of the two universities in São Carlos, the Federal University and the State University, this one here. So that's how we started the CERTEV. So this faculty here belong to two different universities, and as I said, a third university is Marcelo Nalim, our sister university, 30 kilometers from here. So what we do at the CERTEV, we do science and technology. This was compulsory, you know. The funding agency, when we submitted the proposal, we had 3 feet or 3 arms, one in science, one in technology, one in education and dissemination. So Eduardo here, Professor Eduardo, is the technology coordinator. Ana is the education and dissemination coordinator. And Helmut and I are the directors, director and vice director of the CERTEV. So the CERTEV, we work, this is the original proposal, on structure, glass structure, dynamic processes, diffusion, phase separation, relaxation, viscous flow, and crystallization. And ionic conductivity, diffusion process, dynamic processes, and then properties. So the idea is to have structure, dynamics, properties, correlations. Now, this is the fundamental part. We also have an applied part, technology part, armor, dental, construction materials, implants, biomaterials, batteries, laser materials, and catalytic converters. So this is our applied science part of the CERTEV. Now, my own lab, this is my own research, and I will stop here, this is a way I found to show what we do. My very first paper, I started doing research, as I said, as an undergrad in 1976 on glass. And then before that, I worked a little bit on computer science. I had an internship on computer science before doing glass research. That's why I like molecular dynamics, you know, machine learning, these kind of things. My very first paper was published in 1978. Unfortunately, it was published in Portuguese. Nobody reads that paper. It's not even at Scopus, you know. But I keep, you know, that was my first paper anyway, on the fundamentals of crystal nucleation, crystal growth, glass forming ability, overall crystallization. This is the kind of things that I still love, understanding the fundamentals of crystallization processes. So this is a schematic plot. So the first paper was published here. So we have about 250 papers on this particular topic, I think, along the years. And then, of course, if you understand the basics, that's the nice thing about science, you can, at least in principle, develop useful materials. And we then started to work on glass ceramics, because glass ceramics are made by controlled crystallization of glasses. So my first glass ceramic paper was published here in 1996, and we keep doing work on glass ceramics, different types of glass ceramics, dental glass ceramics, bioactive glass ceramics. Yes, you're going to see lectures on this along the week, and these kind of things. Of course, there's a special line of work which includes glass ceramics, but includes a lot of glasses too, and we developed two very interesting bioactive glasses. There's the famous 45S5, but we have a very, not so famous, but still well-known glass called biosilicate, was invented here. And then we have the F18, which is a bioactive glass that can be easily made into fibers. It's very resistant against crystallization. We designed it to be resistant against crystallization, to be able to make fibers and sintered materials, for instance. It's still very active. And finally, not long ago, we started to work on artificial intelligence with Daniel Kazar. He was a student here. He'll give a talk on machine learning on Thursday, I think, this week. And we started to work on machine learning because glasses are ideal for machine learning. Because of the lack of microstructure, you can, in principle, correlate the properties with the chemical composition. You cannot do that for a glass ceramic because there's an extra level of interaction there, which is the microstructure. Chemical composition, microstructure, and then properties. For glasses, in principle, you could get that kind of information. And if you're able to do decent training with a lot of glasses, you can do the inverse process and design new compositions with combinations of properties. For instance, you want a glass with very high elastic modulus, very high TG, low density, and low CTE. How can you do that? Machine learning. Machine learning. Anyway, I'm going to stop here because along this week, you're going to see lots of things about machine learning, about bioglasses, about glass ceramics, and the fundamentals of crystallization in glasses. So thank you very much. With that, I will stop the introduction of the professors, but in the afternoon, it will be your turn to introduce yourselves. You have to introduce yourselves, but unfortunately, you have only 1 minute. Not fair, I know. You have only 1 minute. This is an elevator talk. You have 1 minute to sell your product. And then you have half an hour in the poster session today, Thursday, and Friday. So, thank you very much for coming here. The 3 guides, Professor Ben, Ricardo, and Caio, will guide you to 3 different restaurants. If you come with 70 people at once, it'll be a mess. So, yes.
Just on that, a couple of you were asking for the vegetarian options. And for today, I would recommend if you have vegetarian dietary, you would follow Ricardo. Raise your hand, yeah. So Not only, it's a great restaurant, but specifically. Anyway, thank you.
So guys, please do your best. What time is it now, please? 12:16. Do your best to be back in 1 hour. 1 hour, because we have a tight schedule. We have other things to do this afternoon and tonight. So try to be back in 1 hour. I know it's very tight. Laurie, just a second. Que horas? 5 horas. É, mais ou menos. O ônibus espera lá. Né? Yeah. The bus will be waiting for you at 5 p.m. So we have to leave here at 10 to 5. 10 to 5, we have to close and walk back to the hotel because the bus will be there at 5 to go to the reception. The bus will leave at 5 from the hotel. Mas você vai estar de carro. If you have a car, there's no hurry. Você pode vir, viu, à noite. Tá? Eu vou avisar o Silvio. Que você não tem crachá, né? Você tem? Ah, então pronto. Tá.
Bom, né? Edgar, o jantar do Parktec é às 7 da noite, é isso?
É, 7 da noite.
7 lá.
É, 7 lá. 7 lá.